Hello children, once again welcome back to Physics with Sanoop. See, in this video, finally we are going to discuss the experimental skills. Okay, strictly according to the updated syllabus. And first we will discuss vernier calipers. And vernier calipers is provided with the jaws to measure external diameter, jaws to measure internal diameter, strip to measure depth of a hole, and all of the above. And see all of the above. Now let's see what we have next. Vernier calipers cannot be used to measure external diameter of a cylinder, internal diameter of a cylinder, diameter of a pin point. Okay, then length of a pin, that also can be measured by vernier calipers. Next, what's the function of upper pair of jaws in the vernier calipers? To measure internal diameter of a vessel. Okay. Now the figure shows a vernier whose least count is 0.1 millimeter with the jaws of vernier are touching each other. The zero error in the vernier calipers. Here see, vernier 0 is on the right side of the main scale 0, and see, vernier reading 5 is coinciding with the one of the main scale divisions. So the zero error must be plus 0.5 millimeter. Okay, see, this reading 5 into least count 0.1. So it is 0.5 millimeter. And now next here also we have to find the zero error, and here the vernier 0 is on the left side of main scale 0, so the zero error is negative. And here also see, the reading 5 on the vernier scale coincides with one of the main scale divisions, so the zero error must be this 5 into least count, that is 0.1 millimeter, and it is negative. So minus 0.5 millimeter. Now what's a vernier constant? It is the value of one main scale division by the total number of divisions on the main scale. No, vernier constant means it is the least count, and it is one main scale division divided by number of divisions on vernier scale, or one main scale division minus one vernier scale division. It is the value of one vernier scale division divided by total number of divisions on vernier scale. That's wrong. It is the difference between value of one main scale division and one vernier scale division. That is the least count, and it is the vernier constant. Okay, see, for least count there are two formulae. See, one is one main scale division minus one vernier scale division, and the second one is one main scale division divided by number of divisions on the vernier scale. Okay. Now see, the size of one main scale division is S units, and size of one vernier scale division is V units, and M vernier scale divisions coincide with the M minus 1 divisions on main scale. So least count is one main scale division minus one vernier scale division, and that is equal to one main scale division divided by number of divisions on vernier scale. Okay. Now see, the vernier scale of vernier calipers has 10 divisions. 1 centimeter on the main scale is divided into 10 equal parts. So each main scale division will be 1 centimeter divided by 10, or see, 0.1 centimeter. Now if 10 divisions of the vernier scale coincide with the 8 small divisions of the main scale, it means 10 vernier scale divisions are equivalent to 8 main scale divisions. So 8 main scale division equal to 10 vernier scale division. Okay, so one vernier scale division will be 8 by 10 main scale division, or 4 by 5 MSD, and the least count is one main scale division minus one vernier scale division, and see, one main scale division minus one vernier scale division is 4 by 5 main scale division. Okay, so 1 minus 4 by 5, that is 1 by 5 main scale divisions. Okay, so this is 1 by 5, that is 0.2, and one main scale division is 0.1, so it is 0.02 centimeter. That is the least count. Okay, this one. Now let's see what we have next. Vernier calipers smallest division of main scale is 1 millimeter, so that is 1 MSD. Vernier scale has 20 divisions, so least count will be one main scale division, that is 1 millimeter, divided by number of divisions on vernier scale, that is 20. So 1 by 20, that is 0.05 millimeter, that is the least count. Okay. 19 divisions of the main scale. When fixed jaw touches a movable jaw, 0 of the vernier scale lies on right of 0 of the main scale. Means the 0 error is positive. And 12th division of the vernier scale coincide with any division of main scale. Okay, so the 0 error is plus 12th division. Okay, and see here the least count is 0.05. So the 0 error will be 12. That is the reading coinciding with any of the main scale divisions into least count, that is 0.05. So we will get 0.6 millimeter. 0 error is positive and it is 0.6. Okay, 0 error is positive and it is 0.6 millimeter. Next, the main scale of vernier calipers is divided into 0.5 millimeter and its least count is to be 0.005 centimeter. Okay, the number of vernier divisions. See, number of divisions on vernier scale equals 1 main scale division divided by least count. Okay, see, 1 main scale division is given as 0.5 millimeter and the least count is given as 0.005 centimeter, means 0.05 millimeter. 0.05 millimeter. Okay, and that we will get 10. Okay, so this is 10. Okay, now let's see, to measure the length of a cylinder, a student uses the vernier calipers whose main scale reads at least 1 millimeter. Okay, that is 1 main scale division, and its vernier is divided into 10 divisions which coincide with the 9 divisions of the main scale. So the least count is 1 main scale division divided by number of divisions on vernier scale, and 1 main scale division is 1 millimeter and number of divisions on vernier scale is 10. So least count will be 0.1 millimeter. Okay. Now see, he observed that when 2 jaws of the instrument touch each other, the 8th division of the vernier scale coincide with any one of the main scale divisions and the 0 of the vernier lies to the right of the 0 of main scale. Means the 0 error is positive and it is 8 divisions. Okay, least count is 0.1. Right? Now see, when he placed his cylinder tightly along its length between the 2 jaws, the 0 of the vernier scale lies slightly to the left of 42 millimeter. Means 41 is completed. Okay, left of 42 means 41 is completed. And the 4th vernier division coincide with a scale division. So vernier scale reading is 4. Okay, so main scale reading is 41 and vernier scale reading is 4 into least count, that is 0.1. Okay, then minus 0 error. Children, what do you mean by this 0 error? See, 0 error means, see here the 0 error is actually 8 units. It means we are starting the measurement. Suppose, see here, this is the length that is to be measured. Okay, now suppose this is of length say 15 units. Okay, if this, see this end is at 0 and the reading at this end is 15, the length will be 15. Okay, now suppose this end is at 8. So the 0 error we see 0 error will be 8. Okay, and this reading will be 23. Okay, so the length will be 23 minus 8. Okay, so 0 error positive means we are starting the measurement from that reading. Okay, and suppose if this is minus 8 means the 0 error is negative. Okay, so the reading here it will be, children, the reading here it will be 7. Okay, 7. Right, then what would be the length? It is, see, 7 minus 8, that will be 15. If there is no 0 error, here the reading will be 15. Okay, if there is positive 0 error 8, reading will be 23. Okay, here we have a positive 0 error and that is 8 units on the vernier scale. Okay, so that should be subtracted from the reading. Okay, so finally we will get, see what do we get? It is 41, that is the main scale reading. Then see, this is the vernier scale reading that is to be added with the main scale reading. Okay, then the zero error should be subtracted. Finally, we will get 40.6 millimeter or 4.06 centimeter. 4.06 centimeter. Okay, now let's see what we have next. Now see, there are two scales in a vernier calipers. Suppose here in the last question we have got, see, 40.06 centimeter. See, here we have 4.06 centimeter. See, using the main scale, we can see measure that 4 centimeter accurately. But this 0.06 centimeter cannot be measured accurately by using the main scale. For the measurement of such smaller lengths, we require a small scale, that is the vernier scale here we are using. Okay. Now let's see what we have next. The length of a cylinder is measured with the help of a vernier calipers whose 9 divisions of the main scale are equal to 10 divisions of the vernier scale. Okay, smallest division on the main scale is 0.5 millimeter. That is one main scale reading. And number of divisions on the vernier scale is 10. So the least count will be one main scale division divided by number of divisions on vernier scale, that is 0.5 by 10, or we can say 0.05 millimeter. Okay, it's observed that 0 of vernier scale has just crossed 78th. Okay, see, main scale reading is 78 and each division on main scale is equivalent to 0.5 millimeter. So the main scale reading will be 78 into 0.5. 78 into 0.5 means that is 39 millimeter on the main scale. And see, its fourth division coincides with any main scale division. So 4 is the vernier scale reading. So 4 into least count is 0.05 millimeter. So we will get 39.2 millimeter. 39.2 millimeter. Okay. Now in an experiment, the angles are required to be measured using an instrument. 29 divisions of the main scale exactly coincide with the 30 divisions of the vernier scale. So number of divisions on vernier scale, that is equal to 30. If the smallest division of the main scale is half a degree, means 1 degree is equivalent to 60 minutes. So half a degree will be equivalent to 30 minutes. Okay, and number of divisions on vernier scale is 30. So least count will be one main scale division divided by number of divisions on vernier scale, that is equal to 1 minute. 1 minute. Okay. Now see, capital N divisions on the main scale of a vernier calipers coincide with the n plus 1 divisions of the vernier scale. If each division of main scale is A units, then the least count of the instrument is. See, least count is one main scale division divided by number of divisions on vernier scale. Here each main scale division is A and number of divisions on vernier scale is n plus 1. So the least count will be A by n plus 1. Okay. Now let's see what we have next. A vernier calipers having one main scale division equals 0.1 centimeter, or it is 1 millimeter, is designed to have a least count of 0.02 centimeter. Okay, if n be the number of divisions on vernier scale and m be the length of vernier scale, then okay, see, least count is actually one main scale division minus one vernier scale division. So one vernier scale division will be one main scale division minus least counts. Okay, so one vernier scale division, that is each main scale division is 0.1 centimeter and the least count is 0.02 centimeter. So we will get 0.08 centimeter. 0.08 centimeter. Okay. Now see, let m be the number of vernier scale divisions. So one vernier scale division should be 0.08 centimeter. Okay. Now see, the total length of the vernier scale is m and the number of divisions on the vernier scale is n. So each vernier scale division must be m by n. Okay, so 0.08 equal to m by n. So if you divide m by n, you should get 0.08. Okay, so here you will get 0.05 m by n. Here you will get 0.4 divided by 9, that is definitely not 0.08. Here m by n you will get 0.8 divided by 10, that is 0.08. So this must be the correct option. Okay. Now see, the least count of the main scale of vernier calipers is 1 millimeter. Its vernier scale is divided into 10 divisions and coincide with the 9 divisions of the main scale. Okay. See, the least count of the main scale of a means each main scale division is 1 millimeter and there are 10 divisions on the vernier scale. So the least count of the instrument will be see 1 millimeter divided by 10. Okay, so least count of the instrument will be 1 millimeter divided by 10. Okay, so this much millimeter, or this is equal to, let's say, 0.1. Okay, 0.1 millimeter, right? Now when the jaws are touching each other, the 7th division of vernier scale coincide with the main with a division of main scale, and the 0 of vernier scale is lying right side of the 0 of the main scale. Means the 0 error is positive and it is equal to 7. Okay. Now when this vernier is used to measure the length of a cylinder, the 0 of the vernier scale between 3.1 and 3.2 centimeter means the main scale reading is 3.1 and vernier scale reading is 4. Okay, so here the what we are measuring, see, okay, with this vernier used to measure the length of a cylinder. Okay, so if we measure the length of a cylinder, so this is 3.1 centimeter. 3.1 centimeter is actually 31 millimeter. Okay, 31 millimeter plus now 4th division. Okay, so the vernier scale reading will be 4 into least count, 4 into 0.1, that is 0.4. Okay, and see, the 0 error is 7. Okay, reading 7 on the vernier scale. So we have started the measurement actually from 0.7. So from the reading we have to subtract that 0 error. So 31 plus 0.4 minus 0.7, that we will get 30.7 millimeter, or let us say 3.07 centimeter. Okay, this one, right? Now see, the diameter of a cylinder is measured using vernier calipers with no 0 error. It's found that the 0 of the vernier scale lies between 5.10 centimeter and 5.15 centimeter. See, one division is marked as 5.10 and the next as 5.15. So each main scale division is 0.05 centimeter. Okay, that I have written here. Now see, the vernier scale has 50 divisions spread over a length 2.45 centimeter. So each vernier scale division will be 2.45 by 50. Or if we double both the numerator and denominator, we will get 4.9 divided by 100. So each vernier scale division will be 0.049 centimeter. And the least count is always one main scale division minus one vernier scale division, and that will be 0.05 centimeter minus 0.049 centimeter. And least count we will get 0.004 centimeter. Okay, least count. Now see, okay, it's found that the 0 of the vernier scale lies between 5.10 centimeter. So the main scale reading is 5.10 centimeter, 5.10 centimeter, and the 24th division of the vernier scale exactly coincide. Means the vernier scale reading is 24 into least count, that is 0.05. Okay, 20 least count, that least count is actually 0.01. Okay, so 24 into 0.01, so that we will get 5.124 centimeter. 5.124 centimeter. Vernier scale reading must be multiplied with least count. Okay, and that product should be added to the main scale reading. Okay, now next is screw gauge. See, first question, the least count of a screw gauge. Actually, least count of a screw gauge is pitch divided by number of divisions on circular scale. And what is the pitch? It is the distance through which the screw advances in one complete rotation. Okay, that is the pitch. Pitch divided by number of divisions on circular scale gives the least count of the screw gauge. So the least count of a screw gauge depends only on the number of circular scale divisions. That's wrong. It depends on pitch also. So we have to identify the incorrect statement. Actually, the first statement itself is wrong. Now, in positive zero error, the zero of circular scale lies below the reference line. That's true. In positive zero error, the zero of the main scale is visible. The screw gauge with a pitch of 0.5 millimeter is more precise than the instrument with a pitch of 1 millimeter. Of course, that's also true. Now let's see what we have next. For the pitch of a screw gauge 0.1 centimeter and 200 divisions on circular scale, the least count will be. Least count is actually pitch divided by number of divisions on circular scale. So here pitch is 0.1 centimeter, or we can say 1 millimeter, divided by number of divisions on circular scale is 200. So that is, see, multiply both the numerator and denominator by 5. So we will get 5 millimeter over 1000. So 0.005 millimeter. Okay, 0.005 millimeter. Right? The screw gauge has least count of 0.005 millimeter and its circular scale is divided into 100 equal divisions. What is the distance between two consecutive threads of its screw? Means it is the pitch. Okay, so pitch is actually least count into number of divisions on circular scale, and least count is 0.005 and number of divisions on circular scale is 100, so it is 0.5 millimeter. 0.5 millimeter. Okay, now see what is the reading of micrometer screw gauge shown in figure. Number of divisions on circular scale is 50. See here the main scale reading is that is actually 2, and see circular scale reading is 30. Okay, circular scale reading is 30, and see least count is actually, see here each division is 0.5 millimeter. So one main scale division is 0.5 millimeter and number of divisions on circular scale is given as 50. So the least count will be 0.5 millimeter over 50. So that will be 1 by 100 or 0.01 millimeter. Okay, now the reading, that is main scale reading plus circular scale reading into least count. Main scale reading is 2 and circular scale reading is 30. So 30 into least count 0.01 will be, that is 2.3 millimeter. Okay, 2.3 millimeter. Next, the pitch of a screw gauge is 1 millimeter and there are 100 divisions on its circular scale. So we can easily find the least count, that is pitch over number of divisions on circular scale. So it will be 1 millimeter over 100. So 0.01 millimeter is the least count. Okay, now during the process of finding the zero error, a student finds that the zero of the circular scale lies 4 divisions below the reference line. Means the zero error is plus 4. When an experimental steel wire is placed between two studs, 2 main scale divisions are clearly visible, means main scale reading is 2. And 57 divisions on circular scale are observed. So the circular scale reading is 57, but we have a zero error of plus 4. So main scale reading 2 plus circular scale reading 57 minus zero error, that is 57 minus 4, that should be multiplied with the least count. Okay, so we will get 2.53 millimeter. 2.53 millimeter. Now the pitch of a screw gauge is 1 millimeter and there are 50 divisions on its cap. When nothing is put in between the studs, 44th division of the circular scale coincides with the reference line and 0 of the main scale is not visible. See, 44th division of the circular scale coincides with the reference line and 0 of the main scale is not visible. So the zero error is actually see minus 6, because there are only 50 divisions and 44th division coincides with the reference line, means the zero error is negative 6. Okay, and least count will be pitch divided by number of divisions on circular scale, that is 1 over 50, and it will be 0.02 millimeter. And see, when a glass plate is placed between the studs, the main scale reads 3 divisions. So the main scale reading is 3 and the circular scale read is 26. Okay, so 26 minus 0 error. So 26 minus 6. So 26 plus 6. Okay, that is to be multiplied with the least count. So this is 32 into 0.02 will be 0.64. So 3 plus 0.64. Okay, so that will be 3.64 millimeter. Now, two full turns of the circular scale of screw gauge cover a distance of 1 millimeter. So, one turn will cover a distance of 0.5 millimeter, or the pitch is 0.5. Okay, the total number of divisions on circular scale is 50. So, the least count will be pitch divided by number of divisions on circular scale. So, 0.5 by 50 millimeter. So, that is 1 by 100 or 0.01 millimeter. Okay, further it's found that a screw gauge has a zero error of minus 0.03 millimeter. While measuring the diameter of a thin wire, a student notes the main scale reading of 3 millimeter and the number of circular scale divisions in line with the main scale is 35. Okay, so main scale reading is 3 and circular scale reading is 35, and zero error is to be subtracted. So 35, then this zero error is actually 3 units because each unit each division is 0.01 millimeter. So 35 plus 3 will be the total reading of the circular scale. That is to be multiplied with the 0.01. See, this zero error minus 0.03 means zero error is 3 divisions on circular scale and it is negative. Okay, here the circular scale reading is 35. So the total will be 35 minus 3. Okay, into least count. So we will get 3.38 millimeter. This one. Okay. Now a screw gauge gives the following reading when used to measure the diameter of a wire. Main scale reading is 0 millimeter. Circular scale reading is 52 division. Given that 1 millimeter on main scale corresponds to 100 divisions of the circular scale. Okay. See, so least count will be 1 millimeter divided by number of divisions on circular scale, that is 0.01. Main scale reading here it is 0 and circular scale reading is 52. It is to be multiplied with the least count. So we will get 0.52. Okay, so diameter will be 0.52 millimeter or 0.052 centimeter. 0.052 centimeter. Next, a screw gauge with a pitch of 0.5 millimeter and circular scale with 50 divisions. So least count will be 0.5 over 50 or 1 by 100 or 0.01 millimeter. Okay, that's used to measure the thickness of a thin sheet of aluminum. Before starting the measurement, it's found that when the anvil and screw are in contact with each other, see, 45th division coincides, means the zero error is as there are only 50 divisions and 45th division coincides with the reference line, zero error is minus 5 divisions. Okay, and okay, minus 5 divisions, that is zero error. Okay, with the main scale line, and that the zero of the main scale is barely visible. Okay, what is the thickness of the sheet if the main scale reading is 0.5 millimeter and 25th division? Okay, 25th division and zero error is minus 5, 25 minus 5, that will be 30. Okay, into least count, 30 into least count will be 0.3, 0.3. So 0.5, okay, plus 0.3, that will be 0.8 millimeter. Okay, this one, right? Now, when the gap is closed without placing any object in the screw gauge whose least count is 0.005 millimeter, fifth division on circular scale coincides with the reference line on main scale. So, this zero error is plus 5. Okay, fifth division coincides, right? When a small sphere is placed, reading on the main scale advances by 4 divisions. Okay, so main scale reading is 4 divisions, whereas circular scale reading advances to 5 times to the corresponding reading when no object was placed. See, when no object was placed, see, the reading was 5 divisions. Now it is 5 times, means it must be 25 divisions. Okay, circular scale reading is 25 divisions and zero error is 5. So circular scale reading will be 25 minus 5. That is to be multiplied with the zero error. So we will get 0.1 millimeter. That's to be added with the main scale reading. So it is 4.1 millimeter. That is the diameter. So radius will be half of it, 2.05 millimeter. 2.05 millimeter. Okay. Now a student measured the length of a rod and wrote it as 3.50 centimeter. Which instrument did he use to measure it? See here, the least count is actually 0.01 centimeter. Okay, 0.01 centimeter is the least count. A screw gauge having 100 divisions in the circular scale and pitch 1 millimeter, its least count will be 0.01 millimeter, means 0.001 centimeter. But here we have used an instrument with a 0.01 centimeter. Okay, so this is not the right option. And the second is screw gauge having 50 divisions in the circular scale and pitch as 1 millimeter. So it's an instrument with a 0.02 centimeter least count. Okay, a meter scale, the least count is 1 millimeter. So it is equivalent to 0.1 centimeter. But here we have used an instrument with a least count of 0.01 centimeter. Now finally, a vernier caliper having 10 divisions in vernier scale matches with 9 divisions in the main scale, and main scale has 10 divisions spread over 1 centimeter. So this is one main scale division, that is 0.1 centimeter, divided by number of divisions on vernier scale, that is the least count, and it is equal to 0.01 centimeter. So see, this must be the instrument that is used for this given measurement. Okay. Now the pitch and the number of divisions on the circular scale for a given screw gauge are 0.5 millimeter and 100 respectively. When the screw gauge is fully tightened without any object, the zero of its circular scale lies 3 divisions below the mean line. Means the zero error is plus 3. The readings of the main scale and circular scale for a thin sheet are 5.5 millimeter and 48 respectively. So the thickness will be, actually least count is 0.5 divided by 100, that is 0.05 millimeter, zero error is plus 3, and main scale reading is 5.5, and circular scale reading is 48 minus zero error, that is 48 minus 3 into least count. Okay, so this is 45 into 0.005. Okay, so we will get 5.725 millimeter. 5.725 millimeter. This must be the correct option. Okay, least count of the main scale of a screw gauge is 1 millimeter, and the minimum number of divisions on its circular scale required to measure 5 micrometer diameter of a wire. Means the least count must be 5 micrometer. Okay, so number of divisions on circular scale, that must be pitch divided by least count. 5 micrometer means 5 into 10 raised to minus 3 millimeter, and pitch is given as 1 millimeter. So there must be 1 millimeter divided by 5 into 10 raised to minus 3 millimeter, that much divisions on circular scale, and it is 200. Okay, 200. Right. Now let's see. Using screw gauge of pitch 0.1 centimeter and 50 divisions on the circular scale, the thickness of an object is measured. It should correctly be recorded as, here least count is actually 0.002 centimeter. Means the reading must be an integral multiple of this one. Okay, see here we have an odd number at this place. Okay, here also odd number, here also odd number. So none of the first 3 can be measured by using this instrument. Okay, so the reading must be 2.124 centimeter. Okay. Now let's see what we have. See, in an experiment to find out the diameter of wire using screw gauge, the following observations were noted. Screw moves 0.5 millimeter on main scale in one complete rotation. Okay, that is the pitch. Total divisions on circular scale is 50. So we can easily find the least count, that is 0.5 by 50 or 0.01 millimeter. And see, main scale reading is 2.5, and 45th division on circular scale is in pitch line, that is the circular scale reading. Instrument has 0.03 millimeter negative error. Okay, means 3 divisions has 0 error. Okay, so it must be main scale reading 45. Then this circular scale reading is 45 into least count. Okay, then 0 error must be subtracted. So we will get 2.98 millimeter. 2.98 millimeter. Next, simple pendulum. Dissipation of energy by plotting graph between square of amplitude and time. See, first question, which of the following changes with time when damping is considered for a simple harmonic motion? Time period will not change, angular frequency will not change, but amplitude will change definitely, and energy also. So 3 and 4 means this must be the correct option. Now let's see what we have next. Which of the following represents the correct graph for the amplitude with the time for a damped simple harmonic motion? See, the amplitude decreases or decays exponentially. See, according to the equation, A equals A0 e raised to minus B by 2mt, where A0 is the initial amplitude, B is the damping constant, M is the mass of the oscillating body. So it decreases exponentially means amplitude will become zero only after infinite time. So this must be the correct option. Okay. Now let's see what we have next. Which of the following represents the graph for energy with time for a damped simple harmonic motion? Here also the variation is exponential. Okay, so it decreases to zero only after infinite time. So this must be the correct option. Okay. Next, see, the amplitude of damped simple harmonic motion becomes half in 1 minute and 1 by x times in 3 minutes. The value of x will be. See, this is the variation of amplitude with the time. B, as I have told you earlier, this B is the damping constant, M is the mass of the oscillator. That B by 2m is a constant and it can be replaced by C. C is an arbitrary constant. So A equals A0 e raised to minus CT. That variation is exactly similar to the variation of number of nuclei remaining undecayed in a sample of radioactive nucleus. See, this is N, the number of nuclei present in the sample. N0 is the initial number of nuclei, and e raised to minus lambda t. Lambda is the damping constant. See, in this case we can apply the concept of half-life. Means the time in which the number of nuclei becomes half of its initial value. Just like that, see, here also we can apply the concept of half-life. Here it is given that amplitude becomes half in 1 minute. Okay, so we can take that 1 minute as the half-life of this one. Okay, so the number of or the quantity that remains after n half-lives. Okay, the fraction of the quantity that remains after n half-lives, that is 1 by 2 whole raised to n, where n is the number of half-lives. Here A is the amplitude, okay, and A0 is the initial amplitude. So after n half-lives, the amplitude A is given by A by A0, that is half whole raised to n, where n is the number of half-lives. Okay, see, 1 minute is the half-life. So 3 minutes means the number of half-lives will be 3. Okay, so we can write A by A0 1 by 2 whole raised to number of half-lives, that is 1 by 8. So A0 by 8. It's given that 1 by x times. As it becomes 1 by 8 times, the value of x is 8. Okay. Now let's see if the amplitude of simple harmonic motion becomes 1 by 27 times in 6 minutes. Okay, the amplitude is given by A equals A0 e raised to minus CT. Okay, and T is 6 minutes it's given. So A by A0 will be 1 by 27. Okay, and the amplitude becomes 1 by n times in 4 minutes. Okay, so this 1 by 27 is e raised to minus c whole raised e raised to minus c into 6. Okay, it can be written as this 1 by 27 as 1 by 3 whole cube and e raised to minus 2c whole cube, that is e raised to minus 6c. Okay, so if we take cube root on both sides, we will get e raised to minus 2c equal to 1 by 3, right? E raised to minus 2c equal to 1 by 3. Now after 4 minutes, the ratio of the amplitude to the initial amplitude, it will be A by A0, that is e raised to minus 4c, and it can be written as e raised to minus 2c whole square. Okay, e raised to minus 2c whole square. And here we have e raised to minus 2c equal to 1 by 3. Whole square will be 1 by 9. and here it is given as 1 by n times, so n should be 9. Okay, this one. Now let's see what we have next. If in damped oscillation, the amplitude after 50 oscillations is 0.8 A0, where A0 is the initial amplitude, then the amplitude after 150 oscillations. See, we have A equals A0 e raised to minus Ct. If t is the time required for 50 oscillations, okay, then e raised to minus 50c is 0.8. Okay, then what would be the amplitude after 150 oscillations? Means e raised to minus 150c we have to evaluate. It can be written as e raised to minus 50c whole cube, and e raised to minus 50c we have 0.8, whole cube will be 0.512. So it must be 0.512 A0. Okay. Now meter scale, the mass of a given object by the principle of moments. Okay. Now see the first question, the center of mass of a system of two particles divides the distance between them in inverse ratio of square of masses of particles. Okay. Now see, we have a two particle system with masses m1 and m2. Okay, suppose here is the center of mass. Okay, now let's take the position of the center of mass as the origin. Okay, now see, if you take this as the origin, the coordinate of the center of mass will be 0. Okay, how do you find the position of the center of mass? It is m1r1 plus m2r2 divided by m1 plus m2. That is the position of the center of mass. Here we have chosen that as the origin, so the coordinate will be 0. Okay, if r1 is the distance of the first particle of mass m1 from the center of mass, its coordinate will be minus r1 as it is on left side of the center of mass, and the coordinate of this will be plus r2. Okay, so the coordinate of the center of mass is given by m1 r1 plus m2 r2 divided by m1 plus m2, so we will get m1 r1 equal to m2 r2. See, if P1 V1 equal to P2 V2, usually we write PV equal to constant. Similarly, here we can write MR equal to constant, where R is the distance of the mass M from the center of mass. So R, that is proportional to 1 by M. Or we can say the distance of the center of mass from a given mass varies inversely with the mass. Okay, so when the mass is more, or see, the center of mass will be closer to a heavier mass. Okay, now in inverse ratio of square of masses of the particles, no. Direct ratio, no. Inverse ratio of masses of particles. Okay, this must be true, right? Next, let's see. A system consists of masses capital M and small m. Just I have told you, center of mass will be closer to the heavier mass. Okay, the center of mass of the system at the middle, nearer to capital M, because capital M is much greater than small m. Okay, center of mass must be closer to the heavier mass. Okay, person of mass small m is standing on one end of a plank of mass capital M and length capital L and floating in water, and we have in this case we have to neglect the resistance due to water. Okay, now the person moves from one end to the other end and stops. The displacement of the plank is, see, here we have to consider only the motion along the horizontal. See, the person and the plank together is considered as the system, and there is no, see, along the horizontal direction there are only forces exerted by the man on the plank and the plank on the man, or the forces are only internal along the horizontal direction. There is no external force acting on the system along the horizontal direction. So along the horizontal direction, the velocity of the center of mass will be constant, or acceleration of the center of mass will be 0. Initially, man is at rest and plank is also at rest. So the velocity of the center of mass is given by m1 v1 plus m2 v2 divided by m1 plus m2. Suppose m1 is the mass of the man, its velocity is 0. m2 mass of the plank, its velocity is also 0. So velocity of the center of mass will be 0. So initially the center of mass is at rest, and as the man walks over the plank, there is no external force acting on the system along the horizontal. So there won't be any acceleration for the center of mass, or the velocity of the center of mass will not change. Means the center of mass will remain at rest because initially it is at rest. So the man will move, the plank also will move, but the center of mass will remain at rest. So the displacement of the center of mass will be zero. And see, this is the displacement of the center of mass, m1 s1 plus m2 s2 divided by m1 plus m2, where s1 and s2 are the displacements of the man and the plank. Okay, as the center of mass remains at rest, this must be 0. Okay, so numerator should be 0. Okay, so m1 s1 plus m2 s2 equal to 0, or we can write s1 by s2 equal to minus m2 by m1. Minus m2 by m1. S1 is the displacement of the man. S2 is the displacement of the plank. Capital M is the mass of the plank and small m is the mass of the man. Okay, now see, as there is no external force acting on the system, man exerts a force on the plank and the plank will exert an equal reaction on the man. So the man will be moving in the forward direction and plank in the backward direction. Okay, now see, this is the situation. Initially, this is the position of the plank and this is the position of the man. As the man reaches the other end of the plank, see, by that time, the plank itself must have moved backward by some distance, say S2. So when the plank is considered as the reference, see, man has moved from one end of the plank to the other end. So the displacement of the man with respect to the plank is the length of the plank, that is capital L. And with respect to ground, see, initially man was here and finally he is here. Okay, so with respect to ground, his displacement is S1. And with respect to ground, the displacement of the plank is S2 in the opposite direction. So relative displacement of the man with respect to plank will be S1 minus S2, or it must be S1 plus S2. Okay, that is capital L. See, S1 and S2 together is capital L. Okay, so this capital L is to be divided into S1 and S2, and they must be in the ratio capital M is to small m. And this negative sign is only to show that the displacements are in opposite directions. Okay, so total displacement capital L is to be divided in the ratio capital M is to small m, means it must be divided into capital M plus small m equal parts. So each part must be capital L divided by m plus m. Okay, capital L divided by m plus m. This is the length of each part. And the displacement of the plank we have to determine. Means S2 we have to find out. That must be small m part. Okay, each part is capital L divided by capital M plus small m, and displacement of the plank is small m parts. Okay, so it is small m capital L divided by capital M plus small m. Okay, so this must be the correct option. Next, two particles of mass 5 kg and 10 kg respectively are attached to the two ends of a meter scale with negligible mass. The center of mass of the system from the 5 kg particle is nearly at a distance of. See, if you want to find the distance of the center of mass from a particular mass, the easiest way is to choose the position of that mass as the origin. Here we have to determine the distance of the center of mass from 5 kg mass. So it's better to choose the position of 5 kg as the origin. So its coordinate will be 0. Okay, and see, then the coordinate of the center of mass will be the distance from the 5 kg mass. Okay, see, this is the expression for the coordinate of the center of mass. M1 is 5 kg and its position coordinate is 0. Okay, M2 is 10 kg and its position coordinate is 1 meter. Okay, divided by M1 plus M2 will be 15. Okay, so we will get 2 by 3 meter, and it can be converted into centimeter by multiplying with 100. So 66.666 centimeter, or approximately 67 centimeter. Now in an experiment with meter scale, an unknown mass m is balanced by two non-masses of 16 kilogram and 4 kilogram as shown in figure. Find m. Now see it's pivoted at these points. So let's find the moment about that point. Okay. So when you consider this 16 kilogram, see the distance from the reference point is L1. And if you fix this beam at this point and pull this end with this much force, the turning effect will be like this, or counterclockwise turning effects. And how do you find the turning effect? Force into lever arm means perpendicular distance from the reference points to the line along which the force is acting. Here the 16 kilogram force is acting along this line, and the perpendicular distance to this line from the reference point is this much, or here it is given as L1. Okay, so the counterclockwise turning effect due to this 16 kilogram force will be 16 into L1. And see, if you fix at this point and if you exert a force like this at this end, it provides a clockwise turning effect, and it is given by, here the mass is m and the lever arm is L2, ml2. This is clockwise turning effect and this is counterclockwise turning effect. In order to keep that beam horizontal, these two must be balanced. Okay, now let's consider the second case. Here the unknown mass is shifted to the other side. Okay, so in order to balance it, this we have to keep a 4 kilogram mass here. Then here it provides a counterclockwise turning effect and it is ml1. And see, it is being balanced by this one, it is 4l2. Okay, now if you divide these two equations, you will get m over 16, that is equal to 4 over m. So m square will be 16 into 4 and m will be under root 16 into 4, that is 8 kilogram. Okay, this must be the correct option. Now let's see, a uniform meter scale is in equilibrium position. Calculate the mass of the scale. Okay, uniform meter scale means its whole mass may assume to be concentrated at the center, means at the 50 centimeter mark. Okay, now the scale is pivoted at 30 centimeter mark. Okay, the weight will be acting through the center of gravity, which is located at the geometrical center as the scale is uniform. Okay, and suppose the mass of the scale is m, so the weight mg will be acting along 50 centimeter mark. Okay, and here we have a 40 gram force acting at 30 centimeter mark, acting at say 15 centimeter mark, and it is pivoted at 30 centimeter mark. Okay, so this 40 gram force will provide a counterclockwise turning effect with respect to this fixed point. Okay, and weight of the scale will provide a clockwise turning effect. These two should be balanced. See, this whole length is 30 centimeter and this much is 15 centimeter. So the remaining will be again 15 centimeter. So this counterclockwise turning effects will be 40 gram force into 15 centimeter. And see, the clockwise turning effect provided by the weight of the meter scale, that will be m gram force into distance will be, see, this is at 30 centimeter and the weight is acting through 50 centimeter mark. So this lever arm will be 20 centimeter. So m into 20. So m we will get 30 gram. So the mass of the scale must be 30 gram. Okay. Now see, we have another beautiful example, that is figure shows a uniform meter scale weighing 200 gram force. It must be acting through the 50 centimeter mark. Two weights, 300 gram force and 500 gram force, are suspended from the ruler as shown in the diagram. The distance from the midpoint where a 200 gram force should be suspended to balance the meter scale is. So if we find the turning effect about the point of pivots, okay, see, this is 300 gram and this distance is 40. So 40 into 300, that will be 12,000, and that is counterclockwise. And here we have 500 and this is at a distance 20 centimeter. So 500 into 20 will give you only 10,000. So clockwise turning effect is 10,000, counterclockwise is 12,000. So there must be, see, 2,000 turning effect of magnitude 2,000 must be added to the clockwise direction. Okay, so the 200 gram must be suspended to the right side of the pivot, right? Okay, suppose it is kept at a distance x from the pivot. Okay, so 200 into x will provide a clockwise turning effect. Okay, plus 500 into 20. So the total clockwise turning effect will be 200 into x plus 500 into 20. And counterclockwise turning effect will be, see, this is 300, here it is 10, and the total is 50. So this much will be 40. Okay, so 300 into 40. This is 12,000, and here we have 10,000. When it is taken to the left, 12,000 minus 10,000, that is 2,000 equal to 200x. So x will be 10 centimeter. Okay, this must be the correct option. Next, we have a beam of length 100 centimeter under the effect of three forces as shown in figure. What is the distance of the wedge on beam from 80 gram force so that the beam remains horizontal in equilibrium? Okay, see, with respect to this pivot, with respect to this wedge, see, this 80 gram force will provide a clockwise turning effect, and it will be 80 into lever arm, and the lever arm is x, let it be. Okay, so these two will provide counterclockwise turning effects. See, this 20 gram lever arm will be, see, total distance is 100 centimeter, of which this much is x, so the remaining will be 100 minus x. So the turning effect of 20 gram force will be 20 into 100 minus x, that I have written here, 20 into 100 minus x. Now what about this 50 gram force? See, this much is 20. Okay, so this will be 80 because total is 100. Okay, now see, this much is 80, of which this much is x. So the remaining will be 80 minus x. Okay, so the distance of this 50 gram force from the wedge, that will be 80 minus x, and its turning effect will be 50 into 80 minus x. Okay, here we have 80x, then 50 into minus x will be minus 50x, 20 into minus x will be minus 20x, minus 20x minus 50x minus 70x. When it is taken to the left, it will be plus 70x. Here already we have 80x plus 70x, that will be 150x. And on the right side, see, this is 4,000, 20 into 100, that will be 2,000, 4,000 plus 2,000, that will give you 6,000. Okay, 150x is 6,000, so x will be 40 centimeter. Okay, so this must be the correct option. Next, a uniform meter scale is kept in equilibrium. It is supported at 60 centimeter mark and mass capital M is suspended at 90 centimeter mark shown in figure. What is the relation between the weight of the scale W and the weight of mass capital M? Okay, so the wedge is kept at the 60 centimeter mark. Okay, weight must be acting through 50 centimeter mark as the scale is uniform. Okay, and let the weight of the scale be W, and here a mass capital M is hung at the 90 centimeter mark. Okay, as it remains horizontal, see, W into 10, that is the turning effect due to the weight of the scale, that must be equal to M into 30. Okay, that is the turning effect due to the mass hung at 90 centimeter mark. Okay, now see, W by capital M equal to 3, or we can say W greater than capital M. Okay, W greater than capital M, so this must be the correct option. Now a uniform meter scale is balanced at 60 centimeter mark when weight of 5 gram force and 40 gram force are suspended at 10 and 80 centimeter mark. Okay, respectively, calculate the weight of the meter scale. Okay, see, weight must be acting through 50 centimeter mark, wedge is kept at 60 centimeter. Here we have 40 gram force and here we have 5 gram force. Okay, so the turning effect due to this 5 gram force and weight of the scale will be counterclockwise, and it must be balanced by the turning effect due to this 40 gram force. Okay, so this 40 gram, this much distance is 20 centimeter, that I have written on the right side, 40 into 20. And on the left side, see, this is 50 to 60 means the turning effect due to this W is W into 10, that I have written here, W into 10. and the turning effect due to this 5 gram force will be from 10 centimeter to 60 centimeter, distance is 50 centimeter, okay, and the force is 5 gram force, so the turning effect will be 5 into 50. Okay, here we have this much is 800 and this will be 250, okay, so W into 10, that will be 550, okay, and W will be 55 gram force, okay, so this must be the correct option. Now next, Young's modulus of elasticity of the material of a wire. Okay, see in this case, first question, in the Searle's experiment, following 4 wires are made of the same material, means they must be of the same Young's modulus. Which of these will have the largest extension when the same tension is applied? As they are made up of the same material, all the 4 wires must be having the same Young's modulus, and same tension is also, so capital F is same, Young's modulus is same, so the elongation delta L will be directly proportional to L divided by D square, where D is the diameter, and this A cross-sectional area capital A that I have replaced by pi D square by 4. So, okay, that 4 in the denominator, that is taken to the numerator, okay. So we can say delta L directly proportional to L by D square. See, the length of all the 4 wires are given in the same units, and their diameters are also given in the same units. So you need not convert, because you need only have to compare the elongations. Okay, so you just find the ratio L by D square. In the first case, say length is 300 centimeter and diameter is 3 millimeter. So 300 by 3 square, that is 100 by 3. And in the second case, length is 50 centimeter and the diameter is 0.5 millimeter. So 1 by 2 square, so it will be 200. In the third case, it is 100, and finally we have 50. So among the 4, the largest elongation or longest elongation will be for the second one. So this must be the right choice. Okay. Now let's see what we have next. Copper of fixed volume capital V is drawn into wire of length L. When this wire is subjected to a constant force capital F, the extension produced in the wire is delta L. Which of the following graphs is a straight line? Okay, now see delta L, that is the elongation, it's given by FL divided by AY, and see multiply both the numerator and denominator by the length of the wire. So in the numerator you will get FL square, and in the denominator there will be ALY. That A cross-sectional area and L is the length of the wire. That product AL can be replaced by the volume. Okay, so this volume is fixed, Young's modulus is fixed, force is also fixed, so we can say delta L directly proportional to square of the length, okay, L square. So you will get a linear relation, or if plotted you will get a straight line graph. See delta L versus L square. Okay, now let's see what we have next. The Young's modulus of steel is twice that of brass. Young's modulus of steel is twice that of brass. Here I have written. Okay, 2 wires of the same length and same area of cross section, one of steel and the other of brass, are suspended from the same roof. Okay, same length and same cross sectional area. If we want lower ends of the wires to be at the same level, means elongation produced in both the wires must be the same. Okay, then only we will have this lower ends at the same level. Okay, then the weights added to the steel and brass wires must be in the ratio. See, force is directly proportional to Young's modulus in this case. Okay, so force applied to the steel must be twice of the force applied to the brass. Weights added to steel and brass must be in the ratio 2:1. Okay, force applied to steel must be twice of that applied to brass. Okay. Next, in a Searle's experiment, 2 wires are made of the same material and have the same volume. First wire has cross-sectional area capital A and the second has cross-sectional area 3A. If the length of the first wire is increased by delta L on applying a force capital F, how much force is needed to stretch the second wire by the same amount? Again, we have the force F is equal to YA delta L by L. if you multiply both the numerator and denominator by the cross-sectional area, okay, in the denominator, if you multiply it by A, we will have AL that can be replaced by the volume. And in the numerator already we have a there. If it is multiplied again by another A, you will get A square. So y A square delta L over capital V. V is fixed. Okay, delta L is same here. Young's modulus is also fixed. So we can say the stretching force directly proportional to square of the cross-sectional area. For the second wire, the cross-sectional area is thrice the cross-sectional area of the first. So the force must be 9 times. Means it must be 9F. Okay. Now in determination of Young's modulus of elasticity of wire, a force is applied and extension is recorded. Initial length of wire is 1 meter. The curve between extension and stress is depicted, then Young's modulus of wire will be. Here extension is plotted along the y-axis and stress in kilonewton per meter square plotted along the x-axis. So the slope of the graph will give you, elongation divided by stress. Quantity along the y-axis divided by quantity along the x-axis. As the graph is a straight line, it will have a constant slope, and that slope is given by tan theta, where theta is the angle made by the line with the positive direction of x-axis. Okay. From this you will get, see, tan theta is this much divided by this much. Okay, see this opposite side, that is from 2 millimeter to 4 millimeter. Okay, means 4 minus 2, that is 2 millimeter, or we can say 2 into 10 raised to minus 3 meter. And adjacent side is this much. See, from 4000 kilonewton per meter square to 8000 kilonewton per meter square. So the difference will be 4000 kilonewton per meter square. 4000 kilonewton means 4000 into 1000, or we can write 4 into 10 raised to 6. So slope will be 0.5 into 10 raised to minus 9. Okay. Now see, Young's modulus is actually stress divided by linear strain. Linear strain is elongation divided by original length. Okay. Now this L will go to the numerator. When that stress is taken to the denominator, it will come as the denominator of the denominator. Or we can rewrite this as length divided by elongation by stress. And this quantity inside the bracket is nothing but the slope of the graph. Okay. So L divided by slope will give you the Young's modulus. Length of the wire is given as 1 meter, and the slope we have got 0.5 into 10 raised to minus 9. 1 by 0.5 is 2, and 10 raised to minus 9, when taken to the numerator, it will be 10 raised to plus 9. So that is 2 into 10 raised to 9 Newton per meter square. Okay. Now let's see what we have next in Searle's experiment for the determination of Young's modulus. When a load of 50 kilogram is added to a 3 meter long wire micrometer screw having pitch 1 millimeter, needs to be given a quarter turn in order to restore the horizontal position of spirit level. Means the elongation is equal to 1/4 of the pitch of the micrometer. Okay. And see, the pitch is given as 1 millimeter, so the elongation will be 1/4 of it, that is 1/4 millimeter. Okay, now Young's modulus is FL divided by A delta L, and the force is given as 50 kilogram force, means 50 into 9.8. Length is given as 3 meter. Cross-sectional area is given here 10 raised to minus 5 meter square. Okay, so it is 10 raised to minus 5. And elongation is 1/4 millimeter, that we can convert to meter by multiplying with the 10 raised to minus 3. Okay. Now see, this 10 raised to minus 3 into 10 raised to minus 5, that is 10 raised to minus 8. When taken to the numerator, it will be 10 raised to plus 8. Okay, this 9.8 also you can consider as 10, so it will be 10 raised to 9. Okay, this 4 when goes to the numerator, it will be 4 into 50, that is 200. Okay, take that 100 into 10 raised to 9 will give you 10 raised to 11. Okay, so 2 will be remaining, 2 into 3, that is 6. So 6 into 10 raised to 11. Okay, approximately. Okay, but we have taken this 9.8 as 10. So the answer must be slightly smaller than 6 into 10 raised to 11. So it must be 5.88 into 10 raised to 11. Okay, a student performs an experiment to determine the Young's modulus of a wire exactly 2 meter long by Searle's method. In a particular reading, the student measures the extension in the length of the wire to be 0.8 millimeter with an uncertainty of 0.05 millimeter at a load of exactly 1 kilogram. The student also measures the diameter of the wire to be 0.4 millimeter with an uncertainty of plus or minus 0.01 millimeter. Take G equal to 9.8 meter per second square exact. The Young's modulus obtained from the reading is. Children, see here you need not evaluate the Young's modulus because here we have 4 options. In all the 4 options, this Young's modulus is given the same value. Okay, so you need not evaluate it. See, this is the expression for Young's modulus. And Young's modulus proportional to 1 by d square L. Okay, what is the power of Young's modulus? That is 1. So 1 into delta y by y. Okay, what is the power of L? That is again 1. So 1 into delta L by L. And what is the power of D? That is 2. So 2 into delta D by D. Okay. And see, error in the measurement of length, measurement of elongation, it is given as 0.05 millimeter and elongation is 0.8. Error in the measurement of diameter is 0.01 millimeter and diameter is 0.4 millimeter. Okay, and this is 0.02 by 0.4, or you can write 0.04 by 0.8. Okay, 0.05 by 0.8, 0.04 by 0.8. Okay, so it will be 0.09 by 0.8. And Young's modulus is given as 2 into 10 raised to 11. So delta y will be, see, this much into y. Y is given as 2 into 10 raised to 11. And the quantity inside the bracket we have got 0.09 divided by 0.8. So this is nearly 0.2 into 10 raised to 11. So 2 plus or minus 0.2 into 10 raised to 11 Newton per meter square. Okay, in the experiment for the determination of Young's modulus by Searle's method, a wire of length capital L equal to 2 meter, diameter 0.5 millimeter, for a load capital M equal to 2.5 kilogram, and extension 0.25 millimeter in the length of the wire is observed. Quantities D, L are measured using screw gauge and micrometer respectively. They have the same pitch 0.5 millimeter and the number of divisions on circular scale is 100. So the least count will be 0.5 millimeter over 100. That will be 0.005. And that is the maximum error that we can expect in the measurement of the distances. Okay, least count. Okay, the contributions to the maximum probable error of Young's modulus measurement is. Okay, see, maximum error that can occur in the measurement of diameter or elongation will be 0.005 millimeter, or that is the least count of the instrument that we have used. Okay, now delta y by y, that is equal to delta L by L plus 2 into delta D by D. So delta L by L is this error contributed due to the error in the measurement of elongation. That we will get a 0.005 divided by 0.25 and it is equivalent to 1 by 50. Okay, and see, contribution to the error in the measurement of Young's modulus due to the error in the measurement of diameter, that is 2 into delta D by D, that is 2 into 0.005 divided by 0.5, that is also 1 by 50. So the contributions are equal. Due to the errors in the measurement of D and L are same, this must be the correct option. Okay. Next, in order to determine the Young's modulus of a wire of radius 0.2 centimeter measured using a scale of least count 0.001 centimeter and length 1 meter measured using a scale of least count 1 millimeter, a weight of 1 kilogram measured using a scale of least count 1 gram was hung to get an elongation of 0.5 centimeter measured using a scale of least count 0.00 1 centimeter. What will be the fractional error in the value of Young's modulus determined by this experiment? Okay, and here is the expression for Young's modulus, and percentage error in the measurement of Young's modulus will be, see the power of R is 2, so you have to write 2 into delta R by R into 100. Okay, then see power of capital L is 1 into delta L by L into 100. Okay, power of mass is again M, so 1 into delta M by M into 100. Okay, and power of the elongation small l will be is again 1, so it is 1 into delta L by L into 100. Okay, so this is the percentage error in the measurement of Young's modulus. Okay, we have substituted the values here, and finally you will get 1.4%. Okay, so this must be the right option. Next, we have a student determine Young's modulus of elasticity using the formula y equals mg L divided by 4b d cube delta. Children, see this is small letter delta and this is capital letter delta. Okay, right. Now see the values are tabulated here. Okay, delta y over y, that is equal to delta m by m plus 3 into delta L by capital L. See that errors are given here. Okay, least count of the respective instruments and observed values are also given, and you put the values and finally you will get 0.0155. So this must be the correct option. Okay. Next, in an experiment of determining the Young's modulus of wire of a length exactly 1 meter, the extension in the length of the wire is measured 0.4 millimeter with an uncertainty of plus or minus 0.02 millimeter. When a load of 1 kilogram is applied, the diameter of the wire is measured as 0.4 millimeter with an uncertainty of, means a maximum error, 0.01 millimeter. The error in the measurement of Young's modulus is delta y is found to be x into 10 raised to 10, and you have to evaluate that x. Okay, now see this is the formula for Young's modulus, and Young's modulus you will get 2 into 10 raised to 11. Okay, then error, a fractional error in the measurement of or evaluation of Young's modulus. This is the fractional error in the measurement of diameter, and this is in elongation. So you can evaluate this, and finally you will get delta y, that is equal to 2 into 10 raised to 10. Here it is given that x into 10 raised to 10. So the value of x must be 2. Okay. Now let's see in an experiment. Okay, to determine the Young's modulus, steel wire of 5 different lengths 1, 2, 3, 4 and 5 meter, but of the same cross-sectional area 2 millimeter square, were taken and curves between the extension and load were obtained. The slope, extension per load, okay, of the curves were plotted with the wire length, and the following graph is obtained. If the Young's modulus of a given steel wire is x into 10 raised to 11, then the value of x is. Okay, this is the formula for Young's modulus, and see that can be written as, when that mg is taken to the denominator, it comes as the denominator of the denominator. Oh, okay. So capital L divided by capital A into L over mg. L is the elongation, capital L is the original length. Again, this can be rewritten like L by mg. Okay, that is the slope. This L by mg is the extension per load. Okay, that is the quantity plotted along the y-axis. And original length, that is the quantity plotted along the x-axis. So this must be quantity along y-axis by quantity along x-axis. That's the slope. Okay, this is cross-sectional area. So Young's modulus will be 1 divided by cross-sectional area into slope. Cross-sectional area is given as 2 millimeter square. See, 1 millimeter square is 10 raised to minus 6 meter square. So 2 into 10 raised to minus 6. Okay, and slope. The slope is actually, see, this that is 1.25 divided by this, that is 5. Okay, 1.25 divided by 5. So 1.25 into 10 raised minus 5 divided by 5, that is 0.25 into 10 raised minus 5, that I have written here. So finally you will get 2 into 10 raised to 11. So it's given as x into 10 raised to 11, so x must be 2. Okay. Next, the maximum load a test wire in Searle's experiment can withstand without breaking when its length is reduced to half of its original length. That maximum load is independent of the length, so it will remain same. Okay. Now see overall changes in volume and radii of a uniform cylindrical steel wire are 0.2% and 0.002% respectively when subjected to some suitable force. Longitudinal tensile stress acting on the wire is. See the volume is given as pi r square L. What is the power of V volume? That is 1. So we can write 1 into delta V by V. See what is the power of R? That is 2. So 2 into delta R by R, and the power of L, that is 1 into delta L by L. Okay. Now see this is the fractional error in the measurement of radius, and this is the fractional error in the measurement of elongation. And delta L by L we can write see delta V by V. Okay, error in the measurement of volume minus 2 into error in the measurement of radius. Okay. So error in the measurement of volume is 0.2% and error in the measurement of radius or diameter will be 0.002%. So this delta L by L, error in the measurement of elongation, that you will get 0.196%. Okay, we have stress that is equal to Young's modulus into strain. Okay, and Young's modulus is given as 2 into 10 raised to 11 and strain is 0.196%. That percentage you can convert to a fraction by dividing with 100. So 0.196 by 100 or 0.196 into 10 raised minus 2. 0.196 into 10 raised minus 2. So this you will get 3.9 into 10 raised to 8. So this one. Okay. Young's modulus of a wire of length capital L and radius small r is y Newton per square meter. If the length is reduced to L by 2 and radius to r by 2, its Young's modulus will be y only, because Young's modulus being a property of the material, it must be independent of the physical dimensions of the wire. So y only, right? When a mass 5 kg is hung on a wire, then extension is 30 centimeter. Take, okay, the work done will be. See, when a mass m is hung from the free end of a wire, suppose the wire gets elongated by L. If K is the force constant of the wire, we can write mg equal to KL. So the force constant will be mg by L. Okay, work done is equal to energy stored in the wire, and that is U equal to half kx square. Okay, K we have mgl by L and elongation as L. Okay, so this will be mgl by 2. Mass is 5 kg, G is taken as 10. Okay, elongation is 30 centimeter, means 0.3 meter. Okay, so it will be 7.5 joule. This must be the correct option. Next, in Searle's experiment, reference wire of cross-sectional area 3 into 10 raised minus 6 meter square can withstand a maximum strain of 10 raised to minus 3. Young's modulus of steel is 2 into 10 raised to 11. The maximum mass the wire can hold. See, Young's modulus is mgl divided by al. Okay. So capital M equal to YA by G into small l divided by capital L. Okay, Young's modulus is 2 into 10 raised to 11 and cross-sectional area is 3 into 10 raised to minus 6. Acceleration due to gravity I have taken 10. Okay, then small l by capital L, that is the strain, and it is 10 raised to minus 3. So we will get 60 kilogram. Okay, 60 kilogram. Now, Young's modulus of the material of a wire is equal to stress required to increase its length 4 times. It's not correct. Stress required to produce unit strain. Actually, Young's modulus is stress by strain. When strain is unity, okay, Young's modulus will be equal to stress. So, stress required to produce unit strain. Okay. A steel wire of diameter 0.5 millimeter and Young's modulus 2 into 10 raised to 11 carries a load of capital M. The length of the wire with the load is 1 meter and vernier scale with 10 divisions is attached to the end of this wire. Next to the steel wire is a reference wire to which a main scale of least count 1 millimeter is attached. The 10 divisions of the vernier scale corresponds to 9 divisions of the main scale. Initially, the 0 of the vernier scale coincides with the 0 of the main scale, means there is no zero error. If the load on the steel wire is increased by 1.2 kilogram, the vernier scale divisions which coincide with the main scale division, means we have to find the vernier scale reading. Okay. Now it's given that elongation is mgl divided by ay. You can substitute the given values and you will get the elongation as 3 into 10 raised to minus 4 meter or 0.3 millimeter. Elongation is actually 0.3 millimeter. Okay. Now this is actually small l, right? Elongation is 0.3 millimeter. Okay. Now that elongation, the vernier scale reading into least count. Least count is actually one main scale division divided by number of divisions on vernier scale, and it is given as 10. Main scale division is 1 millimeter, so least count will be 0.1 millimeter. Okay, vernier scale reading is actually number of divisions into least count. Okay, that is 0.3 millimeter. Okay, vernier scale reading into least count is 0.1. So VSR, vernier scale reading must be 3 units. Okay, so answer must be 3, this one. Now the temperature of a wire is doubled, the Young's modulus of elasticity. See, Young's modulus is FL divided by AL. Now capital L is the original length and small l is the elongation. If you multiply both the numerator and denominator by the original length, on the numerator we will have FL square. In the denominator, A into original length, that will be the volume, into elongation. Okay, now see, when the wire is heated, okay, temperature is doubled. When wire is heated, force remains unchanged. Original length, okay, that's original length is fixed. Original length is also constant. Volume remains unchanged, but the elongation will increase. Okay, L will increase. Okay, when temperature increases, L increases, so Young's modulus decreases. Okay, Young's modulus will decrease, right? A vertical experimental wire in Searle's experiment, steel wire of diameter 25 centimeter and length 2.5 meters, supports a weight of 8,000 kilogram. The change in length, we have to evaluate the elongation. Young's modulus is given as 2 into 10 raised to 11 Pascal. Elongation is FL divided by AY. Okay, capital F is the force, it is equivalent to 8,000 kilogram weight. Means 8,000 into G is taken as 10. Okay, L is the original length, that is 2.5 meter. And the cross-sectional area is pi r square. See, the diameter is 25 centimeter or 1 by 4 meter. And the radius will be half of it, that is 1 by 8 meter. Okay, so the cross-sectional area is pi r square or pi into 1 by 8 whole square. Young's modulus is given as 2 into 10 raised to 11. Okay, now see, this 1 by 8 square means 1 by 64 into 2 will be 1 by 32. Okay, this 3.14 you can take it approximately as 3.2 divided by 32, that will be 1 by 10. Okay, 10 raised to 11 divided by 10 will be 10 raised to 10. Okay, now this 10 raised to 10, here we have a 10 and from here you can take 1000. So total will be 10 raised to 4. In the denominator you have 10 raised to 10. 10 raised to 4 divided by 10 raised to 10 will be 10 raised to 6. When it is taken to the numerator, it will be 10 raised to minus 6. Finally, what remains? 8 into 2.5, that is 20. So 20 into 10 raised to minus 6 means 2 into 10 raised to minus 5. 2 into 10 raised to minus 5 is actually 0.02 into 10 raised to minus 3 or 0.02 millimeter. So elongation is 0.02 millimeter approximately. You can choose the answer that is closest to what we have got, that is 0.021 millimeter. This must be the correct option. Next, surface tension of water by capillary rise and effect of detergents. See the first question, the spherical shape of raindrop is due to density of the liquid. No, see, it is due to surface tension. Next, the property utilized in the manufacture of lead shots. That is also the surface tension of liquid lead. Next, adding detergents to water helps in removing dirty grease stains. This is because it increases the oil water surface tension. No, it decreases the oil water surface tension. That is true. It increases the viscosity of the solution. That is false. Dirt is held suspended surrounded by detergent molecules. That's also true. So B and D must be true. Okay, B and D, right? Now spiders and insects move and run on the surface of water without sinking. This is because elastic membrane is formed on water due to property of surface tension. That's true. Okay. Next, shape of meniscus for a liquid of zero angle of contact is hemispherical. Zero angle of contact. Then a liquid does not wet sides of a solid if the angle of contact is more than 90 degree. Okay, obtuse angle, that is more than 90 degree. Then if wax coated capillary tube is dipped in water, wax is that is actually waterproofing agents. So then water in it will there will be capillary depression. Angle of contact will be more than 90 degree. Okay, depress. Next, two capillaries of same material but of different radii are dipped in a liquid. In one of the capillary, the liquid rises to a height of 22 centimeter and in the other 66 centimeter. The ratio of their radii. See, this is the expression for capillary rise. Okay, T is the surface tension, theta is the angle of contact, R is the radius of the capillary, rho is the density of liquid, and G is the acceleration due to gravity. And here we have two capillaries and they are different only in their radii. So we can say H is proportional to 1 by R. So R1 by R2 will be H2 by H1 and that is equal to 66 over 22. So the ratio will be 3:1. Okay, 3:1. This must be the correct option. Next, if a capillary of radius R is dipped in water, the height of water that rises in it is h and its mass is capital M. If the radius of the capillary is halved, the mass of the water that rises in the capillary will be. See, this force due to surface tension will be always acting tangential to the surface of contact. So, this is the direction along which that surface tension will be acting. Okay, and it is actually the tangential force per unit length. Okay, so T will be acting like this. It can be resolved into two components. Okay, T cos theta will be like this and T sin theta like this. Okay, see this T sin theta, okay, surrounding this tube, all those components will get cancelled and T cos theta will get added up. Okay, so T cos theta is the tangential force acting per unit length and it is acting over the circumference of the tube. So the total force acting upwards, that is actually 2 pi r T cos theta, and that balances the weight of the liquid column inside the capillary tube. Okay, so we can say the mass of liquid inside the capillary tube above the liquid surface, okay, in the container, that will be directly proportional to R radius. Okay, so when the radius is made half, this mass also will become half, m by 2. Okay, now when a capillary tube of glass is dipped into a tube containing mercury, then the mercury level in the capillary goes down because the pressure just below the meniscus, okay, will be more than the atmospheric pressure. Okay, more than the atmospheric pressure. Okay, see, the pressure on concave side will be always more than the pressure on convex sides. Okay, so if we have a surface like this, pressure here will be more compared to the pressure on the other sides. Okay, that is why this is being curved like this. Okay, so pressure on concave side will be always more than the pressure on convex side. Okay. Water rises to a height h in a capillary tube at the surface of Earth on the surface of the Moon, where the acceleration due to gravity is 1/6 of the acceleration due to gravity on the surface of Earth. See, this is the expression for capillary rise, 2t cos theta over rho r rho g, and capillarity proportional to 1 by g. On the surface of earth, the acceleration due to gravity is 1/6. So the capillary height will be 6 times. So it must be 6h. Okay, it must be 6h. Right? Now let's see. Two capillary tubes of same diameters are put vertically, one each in two liquids whose relative densities are 1.6 and 0.6, and the surface tensions are 240 dynes per centimeter and 300 dynes per centimeter respectively. Ratio of heights of liquids in the two tubes, h1 by h2, same angle of contact. See, this is the expression for capillary height. h equals 2t cos theta over r rho g. Then h1 by h2 will be t1 by t2 into rho 2 by rho 1. Okay, T1 surface tension for the first liquid is 240 and for the second it is 300. And density of the second liquid is 0.6 and for the first liquid it is 1.6. Okay, this 240 divided by 300 can be written as 4 by 5. Okay, 5 into 1.6 will be 5 into 1.6, that is 8. 4 into 6, that is 2.4. 2.4 and 8, that we can express as 3 by 10. Okay, 3 by 10. So this must be the correct option. In a surface tension experiment with a capillary tube, water rises up to 10 centimeter. If the same experiment is repeated on an artificial satellite which is revolving around the earth, see, inside an artificial satellite, acceleration due to effective acceleration due to gravity is 0. So we have to find the capillary height in a frame where the effective acceleration due to gravity is 0. See, this is the expression for capillary rise, and see, in that expression acceleration due to gravity comes in the denominator. So when the acceleration due to gravity is 0, this capillary height should be infinite. But the liquid can never rise up to infinity. It will go only up to the brim of the tube, because this capillary rise is primarily due to the adhesive force between the liquid molecules and the solid molecules. So the liquid rises up to the brim of the tube, or we can say full length of the capillary tube. Now, radius of a capillary is 0.2 centimeter. A liquid of weight 6.2 Newton may remain in equilibrium in the capillary. Then the surface tension of liquid will be, it's given that angle of contact, that is equal to 0 degree. See, when angle of contact is 0, see, this is the expression, okay, 2 pi RT, that is equal to mg. So surface tension is given by mg over 2 pi r. So that mg is given as 6.2 Newton, 2 pi, radius is given as 2 centimeter. No, it is 0.2 centimeter, or we can write 2 into 10 raised to minus 3 meter, and we will get 500 Newton per meter. 500 Newton per meter. Okay. Water rise in a capillary up to an extension height such that upward force of surface tension balances the force of 75 into 10 raised minus 4 Newton due to weight of water. If the surface tension of water is 6 into 10 raised minus 2, the internal circumference of the capillary must be. And see, here also this angle of contact is 0. It's given t into 2 pi r equal to weight. When the angle of contact is 0, surface tension will be acting tangential to the surface of the tube. Okay, it is the force per unit length, and it is acting over the circumference of the, or let us say, internal perimeter. Okay, so this is the force per unit length, and this is the total length over which the surface tension is acting. So this force balances the weight of the liquid in the capillary tube. So this internal circumference 2 pi r, we will get W by T, 75 into 10 raised minus 4 divided by 6 into 10 raised minus 2, that is 12.5 into 10 raised minus 2 meter. Okay, 12.5 into 10 raised to minus 2 meter. Internal radius of a capillary tube is 1 by 14 centimeter and surface tension is 70 dynes per centimeter. If the angle of contact is 0, then the water will rise up in the tube up to a height. So we have to determine the capillary height. And 2t cos theta divided by r rho g. And see, here the angle of contact is 0. So cos 0 will be 1. 2, and this surface tension is given as 70 CGS units. Radius is 1 by 14 centimeter. Rho density of water in CGS system is 1, acceleration due to gravity is 980. This 980 divided by 14, that is exactly equal to 70. Okay, so we will get 2 centimeter, right? This one, 2 centimeter. Now water rises in a capillary up to a height of 4 centimeter if it is tilted to 30 degree from the vertical. Okay, when a capillary tube is held like this, then also the capillary height, vertical height up to which the liquid rises will remain unchanged. Okay, so this will be 4 centimeter. Okay, this will be again 4 centimeter, this much. Okay, what is the length of the liquid inside the capillary tube? Means we have to determine this length. Okay, that is actually L by h by cos 30. L equal to h by cos 30. H is given as 4 centimeter, cos 30 is root 3 by 2. So it will be 8 by root 3 centimeter, this much. 8 by root 3 centimeter. The wettability of a surface by a liquid depends primarily on angle of contact between the surface and the liquids. Okay, when the angle of contact is acute, liquid will wet the solid. When the angle of contact is obtuse, liquid cannot wet the solid. And if the angle of contact is exactly 90 degree, then the case will be critical. Okay. Now see, water rises to a height h in capillary tube if the length of capillary tube above the surface of water is made less than h. Then, as I have told you earlier, it will go up to the brim of the, or up to the top end of the capillary tube. So water does not rise at all. Water rises up to the tip of capillary tube and then starts overflowing, never overflows. Okay, water rises up to the top of capillary tube and stays there without overflowing. Okay, that's the right option. 3 liquids of densities rho 1, rho 2 and rho 3 with rho 1 greater than rho 2 greater than rho 3 having the same value of surface tension capital T raised to the same height in 3 identical capillaries, the angles of contact theta 1, theta 2, theta 3 obey. H equal to 2t cos theta divided by r rho g. Okay, here the see here there is capillary rise. Means the angle of contact should be less than 90 degree in all the 3 cases. So theta should be less than 90 degree in all the 3 cases, and see, h is same. Okay, then surface tension is same, then this radius is same. Okay, so we can say cos theta directly proportional to density. Okay, so when density decreases, cos theta will decrease, so theta should increase. Okay, because as theta increases, cos theta decreases. When theta decreases, cos theta increases. So when density decreases, cos theta will decrease, so theta will increase. Okay, so when density is less, theta will be more. Okay, here it is given that rho 1 greater than rho 2 greater than rho 3. So theta 1 less than theta 2 less than theta 3. Okay, and all the 3 angles must be between 0 and 90 degree also. Okay, so this must be the right option. Okay, while performing experiment to measure surface tension of water using capillary rise method, the necessary precautions to be taken is, okay, see, both capillary tube and water should be free from contamination. Capillary tube should be clean while water may contain some desert. This is true, this one first statement. Okay, second is wrong. Temperature of water should be observed while performing experiments. That is also true. Okay, internal diameter of capillary should be measured in 2 mutually perpendicular directions. That is also true. So only the second statement is false. Okay, so correct option should be the third option, A, C and D. Okay. Next, while measuring the surface tension of water by capillary rise method, which of the following precautions are necessary? Capillary tube and water must be clean and free from contamination or grease. That must be true. Capillary tube should be set vertical. The temperature of water should be noted. That's also true. Traveling microscope should be moved in lower direction only to avoid backlash error. That is also true. Internal diameter of capillary tube should be measured in 2 mutually perpendicular directions. So all the statements must be true. Okay, fourth option. Next, See, choose the incorrect statement among the following. Capillary action is due to both cohesion and adhesion. Okay, falling raindrop becomes a spherical due to cohesion and surface tension. Surface tension is due to cohesion between atoms at the free surface. Mixing soap solution with water increases the surface tension. That is a wrong statement. It actually decreases the surface tension. Okay. Next, if an end of a capillary tube is dipped into a liquid, then liquid level will rise in the tube, liquid level depress in the tube, liquid level remain constant as of surrounding liquid. Any of the above may be possible, means it may rise or fall or maybe at the same level. Okay. Now, if the angle of contact of a drop of liquid is acute, then if it is acute, then adhesion is more than cohesion. Okay, adhesion is more than cohesion. Adhesion means that is the intermolecular force between different types of molecules, while cohesion is the intermolecular force between similar type of molecules. Okay. Next, see, 4 capillaries of different bores are dipped in same liquids, okay, contained in a beaker as shown. The increasing order of the respective height attained by the liquid in the capillaries will be, see, only the radius is different in the 4 cases. Okay, and see radius go on decreasing, okay, as we move from left to right. Okay, so as the capillary height varies inversely with radius, okay, then height attained by the liquid, see, increasing order will be A, B, C and D. Okay, this must be the correct option, right? Actually, see, this is the expression, and the capillary height H is proportional to 1 by R. When the radius is less, capillary height will be more. Okay, this is having minimum radius, so the capillary height will be maximum in this case. Okay. Next, the phenomenon of rise or fall of liquid level in a capillary tube is called as capillarity. In non-wetting liquids like mercury, the correct relation between cohesion of mercury and adhesion between mercury and capillary tube is cohesion is actually greater than adhesion. Okay, cohesion greater than adhesion. Why does an ink-filled fountain pen leak at a high altitude? Atmospheric pressure decreases at a high altitude. Then choose the wrong statement from the following. Small droplets of a liquid are spherical due to surface tension. That's true. Oil rises through the wick due to capillarity. Again, that's also true. In drinking liquids through a straw, we use phenomenon of capillarity. That's also true. So the wrong statement is none of these. Okay. Liquid reaches an equilibrium as shown in a capillary tube of internal radius small r. If the surface tension of the liquid is capital T, the angle of contact theta and density of liquid rho, then the pressure difference between points P and Q is. See, actually the point P is just below the meniscus. Okay, and just above the meniscus, it's open to atmosphere, where the pressure is atmospheric pressure and is represented by P with the suffix 0, say P0. Okay, now see, when we take a curved surface, the pressure on the concave side will be always more than the pressure on the convex side. Okay, so here the pressure on the concave side is atmospheric pressure. That should be more than the pressure below the meniscus. Okay. So PO, that is the, or P0, that's the atmospheric pressure, minus PP. Okay, that is the pressure just below the meniscus. That is equal to 2T by capital R, where capital R is the radius of the meniscus. Okay, now this point, consider this point Q and consider a point here where this point is open to atmosphere. So this point and this capital Q are on the same horizontal line in a liquid at rest. So by Pascal's law, the pressure at this point and pressure at Q will be the same. Or let us say the pressure at Q is equal to the atmospheric pressure. Okay, so PQ equal to P0. Okay, because they are 2 points at the same level in a liquid at rest. So see, this P0 can be replaced by PQ. So PQ minus P with the suffix P, that is equal to 2T by capital R, where capital R is the radius of the meniscus. Okay, see here we have capital R radius of the meniscus, small r radius of the capillary tube, and theta is the angle of contact. From this right triangle we will get small r by capital R equal to cos theta. Okay, small r by capital R equal to cos theta. So we can write 1 by capital R equal to cos theta by small r. So PQ minus PP will be 2t by small r into cos theta. 2t by small r into cos theta. This one. Okay. The following observations were taken for determining surface tension capital T of water by capillary method. Diameter of capillary capital D equal to 1.25 into 10 raised to minus 2 meter, and rise of water, that is H equal to 1.45 into 10 raised to minus 2 meter. Okay, T equal to rho Hg divided by 2 into 10 raised to 3 Newton per meter. Possible error in surface tension is closest to. T equal to RHG by 2 it's given, and that R can be replaced by capital D by 2, where capital D is the diameter, so we will get DHG by 4. Then percentage, see power of T is 1, so the 1 into percentage error in capital T. Here the power of D is 1, again 1 into delta D by D into 100, that is the percentage error in the measurement of diameter. Then power of H is also 1, that power here comes here, 1 into delta H by H into 100, percentage error in the measurement of capillary rise. Okay, so if you evaluate this, you will get see 100 by 125 plus 100 by 145, and it is approximately 1.5%, this one. Okay. Next, water rises to a height of 10 cm in a glass capillary tube if the area of cross section of the tube is reduced to 1/4 of its former value. Then find height of water rises in the tube. It's given H equals to T cos theta divided by R rho G. And see, the cross sectional area of the tube is given by A equals pi r square, or we can say radius of the capillary tube is directly proportional to square root of its cross sectional area. And see, from here we can say the capillary height is directly proportional to 1 by r. So h dash by h will be r by r dash, which in turn proportional to square root of the cross sectional area, so under root a by a dash. Okay, now see, area of cross section of the tube is reduced to 1/4, so a dash is a by 4. So if you replace this a dash by a by 4, you will get 4 under root, that is equal to 2. So h dash is equal to 2h, or 2 into 10, that is equal to 20 centimeter. Okay. Next, liquid rises to a height of 2 cm in a capillary tube. The angle of contact between the solid and liquid is 0. The tube is depressed more now, so that the top of the capillary is only 1 cm above the liquid. Then the apparent angle of contact between the solid and liquid is. See, this is the expression for capillary height. H equals 2t cos theta over r rho g. Now we can say H is directly proportional to cos theta. So H dash over H is equal to cos theta dash divided by cos theta, when the height of the capillary tube above the liquid surface is of insufficient length, or when it is less than the capillary height, the angle of contact theta will get adjusted such that h dash by h is equal to cos theta dash by cos theta. And initially theta equal to 0, cos theta will be 1, and cos theta dash will be h dash by h, that is equal to 1 by 2. So theta dash will be 60 degree. Okay, this one. Soap solution should have small angle of contact. The angle of contact is small, therefore soap solution rinse the clothes, the dust in less time. Both A and R are true, and R is the correct explanation of A. Okay. Now assertion: surface tension of a liquid is independent of the area of the surface. Surface tension produced due to cohesive force. Okay, so assertion, both assertion and reason are true, and R is the correct explanation of assertion. The angle of contact of a liquid decreases with the increase in temperature, that is true. With increase in temperature, the surface tension of liquid increases, that is false. So A is true, but R is false. Okay. Now see, we have to match the Angle of contact for a liquid with suitable options in list 2. See, the first is 0 degree. Angle of contact is 0 degree. Then that is pure water and glass. Okay, so one must be matching with the capital D. And angle of contact is 90 degree, pure water and silver. Okay, so 2 must be matching with the capital B. And angle of contact is less than 90 degree or acute, there will be liquid will rise in the tube. So third must be matching with the A. And finally, angle of contact is greater than 90 degree. See, liquid will not wet solids. Okay, so 4C. So 1D, 2B, 3A and 4C. So this must be the correct option. Next, see the coefficient of viscosity of a given viscous liquids by measuring the terminal velocity of a given spherical body. Okay, first see the velocity of falling raindrop attained limiting value because of viscous force exerted by air. Okay. Then Poise is the unit of viscosity. Okay. Then a body of density G1 and mass m is moving downward with a uniform velocity in glycerin of density G2. What is the viscous force acting on it? See, the viscous force acting on it will be equal to apparent weight when it moves with a constant terminal velocity. And apparent weight is actually weight minus upthrust. mg is the weight. Upthrust is equal to weight of glycerin displaced. Okay, see, mass divided by density of body, that is the volume of the body, and it is equal to volume of glycerin displaced, into density of glycerin, that is mass of glycerin displaced, into G, weight of glycerin displaced, and it is equal to upthrust. So weight minus upthrust, that is the apparent weight, and it is equal to the viscous force when it moves with a constant terminal velocity. Okay, so viscous force will be mg into 1 minus d2 by d1. Okay, mg into 1 minus d2 by d1. Two small spheres of radii smaller and 4 times smaller fall through a viscous liquid with the same terminal velocity. The ratio of the viscous forces acting on them. See, viscous force is actually 6 pi eta rv. Both are moving with the same terminal velocity through the same viscous medium. So the force will be directly proportional to the radius. So F1 by F2 will be R1 by R2, that is equal to 1:4. Okay, 1:4, this one. Next, a small drop of water falls from rest through a large height h in air. The final velocity independent, almost independent of h. This one, okay, independent of h. Two drops of equal radius are falling through air with a steady velocity of 1 centimeter per second. If two such drops coalesce, then its terminal velocity will be. See, when n identical droplets combine to form a single drop, then the radius of the resulting drop capital R is n raised to 1 by 3 into small r. This is the expression for terminal velocity. Okay, 2 into rho minus sigma into g divided by 9 eta. Eta is the coefficient of viscosity of the medium through which the sphere is falling. Rho is the density of the sphere and sigma is the density of the medium. Okay, r is the radius of the sphere. So here we can say v directly proportional to r square. So v dash, the terminal velocity of the resulting drop, divided by terminal velocity of the individual drops. Okay, so capital R by small r whole square, and this is n raised to 2 by 3. And see, here we have two drops. So 2 raised to 2 by 3. Or we can split it as 2 square whole raised to 1 by 3 or 4 raised to 1 by 3. So v dash will be 4 raised to 1 by 3 into v, and v is 1 centimeter. So 4 raised to 1 by 3 centimeter per second. Okay, the speed of 4 centimeter radius ball in viscous liquid is 40 centimeter per second. If the speed of 2 centimeter radius, means the radius is reduced to half. Okay, radius is reduced to half. See, terminal velocity directly proportional to square of the radius. So when the radius is reduced to half, speed will become 1/4. The original speed was 40 centimeter per second. Now the speed will be 10 centimeter per second. Okay, this one. Next, two raindrops falling through air have radii in the ratio 3:2. They will have terminal velocities in the ratio. See, terminal velocity directly proportional to square of the radius. So, if the radii are in the ratio 3:2, then terminal velocities will be in the ratio 9:4. Okay, this one. Now, a sphere of mass capital M and radius r is falling in a viscous liquid. The square of the terminal velocity attained by the falling object will be proportional to, that is equal to, see, 6 pi eta rv, that is the viscous force, that is equal to the weight when the body moves with the terminal velocity. So, the terminal velocity v will be directly proportional to m by r. Okay, this one, m by r. Now, a drop of water of radius 0.0015 millimeter is falling in air. If the coefficient of viscosity of air is 2 into 10 raised to 5 kilogram meter second, the terminal velocity of the drop will be, okay, density of water is given and acceleration due to gravity is also given. So this is the expression for terminal velocity. Okay, 2 by 9, then density of water is 10 raised to 3, acceleration due to gravity I have taken 10. Okay, radius is 1 point, what is the radius? Radius is actually 0.0015 millimeter, means 1.5 into 10 raised to minus 6 meter. Okay, and eta, coefficient of viscosity, is given as 2 into 10 raised to minus 5. Okay, now this 1.5 square means it is 2.25. Okay, 2.25 divided by 9, that will be 4 in the denominator. Okay, 4 in the denominator, 2 and 2 can be cancelled. This 10 raised to minus 5, and here we will have 10 raised to minus 12. 10 raised to minus 12 by 10 raised to minus 5 will be 10 raised to minus 7. Into this 10 raised to minus 6, into 10 raised to 3, that is 10 raised to minus 3. Okay, so we will get, see, 1 by 4 into 10 raised to minus 3, or let us say 2.5 into 10 raised to minus 4. 2.5 into 10 raised to minus 4 meter per second. Now, two raindrops reach earth with different terminal velocities having ratio 9:4, then the ratio of their volume. Now see, terminal velocity directly proportional to square of the radius, or let us say radius of the drop is directly proportional to square root of velocity. Terminal velocities are given in the ratio 9:4, so their radii will be in the ratio root of 9 by 4 or 3 by 2. And volume proportional to cube of the radius. So V1 by V2 will be R1 by R2 whole cube. So 3 by 2 whole cube means 27 by 8. This one. Viscosity of liquid decreases with the increase in temperature. Okay, this one. See, when temperature increases, in general, viscosity of liquids will decrease, but the viscosity of gases will increase. Okay. Now, a small sphere of radius r falls from rest in a viscous liquid. As a result, heat is produced due to viscous force. The rate of production of heat when the sphere attains its terminal velocity is proportional to. See, this is the expression for terminal velocity. And here, see, terminal velocity is directly proportional to r square. And the force is proportional to radius as well as velocity, viscous force. Okay, so the power is actually the product of force and velocity. See, this force is proportional to radius and velocity. Okay, multiplied by velocity, we can say this power will be proportional to radius and velocity square. As velocity is proportional to r square, velocity square will be proportional to r raised to 4. And there is one more r here, so finally the power will be proportional to r raised to 5. Okay. Now, two spherical balls having equal masses are made from materials of densities ρ1 and ρ2. It's given that ρ1 equals 8 ρ2 and have radii of 1 millimeter and 2 millimeter respectively. They are made to fall vertically from rest in viscous medium whose coefficient of viscosity equals eta and whose density is 0.1 ρ2. The ratio of their terminal velocities would be. See, expression for terminal velocity is given as 2 rho minus sigma into g divided by 9 eta r square. And here we have two balls of different densities falling through the same viscous medium, and their radii are also different. So we can say V directly proportional to rho minus sigma and r square. So V1 by V2 will be rho1 minus sigma. Rho1 is the density of the first sphere, Rho2 is the density of the second sphere, and sigma is the density of the medium. Okay, so R1 by R2 whole square. See, both this Rho1 and sigma are expressed in terms of Rho2. So this Rho1 can be replaced by 8 Rho2 and sigma can be replaced by 0.1 Rho2. Okay, radii are in the ratio 1 millimeter and 2 millimeter, so 1 by 2 whole square. Here we will get 7.9 Rho2 and denominator will be 0.9 Rho2. Rho2 will get cancelled. So 7.9 into 1 in the numerator and 0.9 into 4 in the denominator, that is 3.6. 7.9 divided by 3.6, or we can express it as 79 by 36. This one. The velocity of a small ball of mass capital M and density d when dropped in a container filled with glycerin becomes constant after some time. If the density of glycerin is d by 2, then the viscous force acting on the ball will be. See, viscous force is actually for this apparent weight. Apparent weight is 4 by 3 pi r cube, that is the volume of the immersed body into density d, mass of the immersed body. Then volume of the immersed body is equal to volume of fluid displaced into density of fluid, that is the mass of fluid displaced. Okay, into G will give you the weight of fluid displaced, or it is the upthrust. So weight minus upthrust, that is the apparent weight. So it is actually this one 4 by 3 pi r cube. See this one 4 by 3 pi r cube dg. Okay, that is the mass of the body. Okay, so mg divided by 2, right? So this must be mg by 2. Okay, this one, right? A spherical ball is dropped in a long column of a highly viscous liquid. The curve, the graph shown, which represents the speed of the ball. See, the speed of the ball will attain a constant value after some time. That constant value is called the terminal velocity, and that is being represented by this curve. Okay, this one. Okay, and that is represented by B. Okay, so this must be the correct option. The correct statement about the variation of viscosity of fluid with the increase in temperature. See, with increase in temperature, viscosity of liquids decreases in general and viscosity of gases increases. Okay, viscosity of liquids decreases, viscosity of gases increases. Okay, this one. The terminal velocity of a copper ball of radius 5 mm falling through a tank of oil at room temperature is 10 cm per second. If the viscosity of oil at room temperature is 0.9 kg meter raised minus 1 second raised minus 1, the viscous drag, okay, that is see, viscous force is 6 pi eta RV, 6 pi 0.9 into 5 into 10 raised minus 3 into 0.1. Okay, see, this we will get, that is, see, 6 pi. What is 6 pi? That is approximately 20. 20 into 5, that is 100. Okay, so this will be 100, then 10 raised to minus 3 and 0.1, that is 10 raised to minus 4 into 100, 10 raised to minus 2. So 9 into 10 raised to minus 3, nearly. 9 into 10 raised to minus 3, nearly. Okay, so it must be 8.48 into 10 raised to minus 3 Newton. If the terminal velocity of a sphere of gold, density is given as 19.5 kilogram per meter cube, is 0.8 meter per second in viscous liquid of density 1.5 kilogram per meter cube, find the terminal speed of a sphere of silver whose density is 10.5. So velocity directly proportional to rho minus sigma. Okay, because they are of the same radius. Okay, and falling through the same viscous medium. So eta is same in both the cases. Radius is also same. So the only quantity that is different is rho minus sigma. So V1 by V, here we are finding V2 by V1. That will be rho 2 minus sigma by rho 1 minus sigma. Okay, so 10.5 minus 1.5, that is 9. 19.5 minus 1.5, that is 18. 9 by 18 means 1 by 2. Okay, so V2 must be V1 by 2. V1 is given as 0.8. So V2 will be 0.4 meter per second. Two rubber ball with radii in the ratio 1:2 fall from a great height through the atmosphere. Then the ratio of their momentum after they have attained terminal velocity is. See, velocity directly proportional to r square and mass directly proportional to volume, which in turn proportional to cube of the radius. Okay, so the linear momentum being the product of mass and velocity must be proportional to r raised to 5. Radii are given in the ratio 1 is to 2, so the linear momentum will be 1 by 2 whole raised to 5 or 1 is to 32 we can say. Okay. Next, consider the following two statements A and B and identify the correct choice in the given answers. Viscosity of liquids decreases with the decrease in temperature means it's a false statement. Surface tension of liquid decreases with increase in temperature. That statement is true in general. So, A is false, B is true. Okay, this one. Now a small ball of mass m and radius r is falling under gravity through a viscous liquid of coefficient of viscosity eta. If g is the acceleration due to gravity, then the terminal velocity of the ball is proportional to. See, 6 pi eta rv is the viscous force acting on a sphere falling through a viscous medium, and this viscous force will be equal to the weight if it attains or when it attains terminal velocity. So we can say velocity directly proportional to mg by r eta. Okay, this must be the right choice. Next, let's see, a sphere of brass released in a long liquid column attains a terminal velocity v0. If the terminal velocity attained by a sphere of marble of the same radius and released in the same liquid is nv0, then the value of n will be, okay, given that the specific gravity means the relative density of brass, marble and liquid are 8.5, 2.5 and 0.8. Actually, relative density is the ratio of density of the substance to the density of water. In CGS system, density and relative density are equal. Now see, this is the expression for terminal velocity. Okay, when we consider the two cases, the only term that is different in two cases is rho minus sigma. Okay, radius is same for both the spheres. Coefficient of viscosity is same, acceleration due to gravity is same. Okay, so n that is equal to, because the terminal velocity in the first case is v0 and in the second case it is n times v0. Okay, let's find the ratio of the terminal velocities. Okay, v2 by v1. So n v0 by v0, that is n. That is equal to rho minus sigma in the second case by rho minus sigma in the first case. Okay, this is 2.5 minus 0.8, that is 1.7, 8.5 minus 0.8, that is 7.7, and we can express it as 17 by 77, this one. Okay, two metal spheres are falling through a liquid of density 2 into 10 raised to 3. With the same uniform speed, the material density of sphere 1 and sphere 2 are 8 into 10 raised to 3 kilogram per meter cube and 11 into 10 raised to 3 kilogram per meter cube respectively. The ratio of their radii. See, this is the expression for terminal velocity. Here we have to consider two cases. Okay, in which in both the cases terminal velocity is the same. Okay, coefficient of viscosity is the same, and see, acceleration due to gravity is same. The factors that are different, the radius and the quantity rho minus sigma. Okay, see, this r square proportional to 1 by rho minus sigma, or we can say r proportional to 1 by root of rho minus sigma. So r1 by r2 will be root of rho 2 minus sigma by rho 1 minus sigma. Okay, rho 2, that is the density in the second case, and it is given as, see, 11 into 10 raised to 3. See, all densities are given in terms of 10 raised to 3. So we are here we have to find only the ratio. So you need not consider that multiplication factor 10 raised to 3, because it comes on all the factors, all the terms, and it will get cancelled. Okay, so 11 minus 2 over 8 minus 2, that is 9 divided by 6, or root of 3 by 2. Root of 3 by 2, this one. Okay, now see, viscosity of liquid is the property of the liquid by virtue of which it opposes the relative motion among its different layers. That is true. Viscosity of liquid increases rapidly with rise in temperature. That is false. So A is true, but R is false. Okay. Now machine parts are jammed in winter. That is true. The viscosity of lubricant used in machine parts increases at low temperature. That is true, and it is also the correct explanation of assertion. Both A and R are true, and R is the a correct explanation of A. Okay. Now, a small spherical ball is dropped in a viscous liquid. The velocity of liquid is shown in figure. The value of acceleration due to gravity in viscous liquid first increases and then becomes constant. Okay, assertion is true, and this reason is the correct explanation of A. This must be true, right? Next, determination of speed of sound in air at room temperature using resonance tube. See, in this first question, a tube closed at one end means it's generally called closed pipe. Okay, and the fundamental frequency is V by 4L. There will be always an anti-node at the open end and node at the closed end. Or air column in a closed pipe can vibrate only with the anti-node at the open end and node at the closed end. Okay, a tube closed at one end and containing air produces, when excited, the fundamental note of frequency 512 means V by 4L is 512. If the tube is open at both ends, the fundamental frequency that can be excited is, for an open pipe, the fundamental frequency is actually V by 2L. For closed pipe, it is V by 4L. Or we can say, see, the fundamental frequency of the open pipe is twice the fundamental frequency of a closed pipe of a given length. Okay, so nu with the suffix O, fundamental frequency of the open pipe, that is 2 into fundamental frequency of the closed pipe, it's given as 512. So it must be 1024. Okay. Next, an air column in pipe which is closed at one end will be in resonance with a vibrating tuning fork of frequency 264 if the length of the column in centimeter is, okay, closed pipe, the fundamental frequency is V by 4L, and we have to find out the length. Okay, see, speed is given as 330 and frequency is 264 Hertz. So length will be this 5 divided by 4 into 4. How do we get that? See, this 330 and see, we can divide with 66. Okay, so in 330, how many 66 will be there? 5. And in 264, 4. Okay, so this is 5 by 4, and here already we have another 4 here. So 5 by 4 into 4, that much meter. And we can convert it into centimeter by multiplying with 100. Okay, so here we will get 31.25 centimeter. 31.25 centimeter, right? Velocity of sound in air is 320 meter per second. A pipe closed at one end has length of 1 meter, neglecting n corrections. The air column in the pipe can resonate for sound of frequency. See, closed pipe nu equal to fundamental frequency is V by 4L, and 3V by 4L is the first overtone and 5V by 4L is the second overtone. Or a closed pipe can vibrate only at see, odd harmonics of the fundamental frequency. Okay, so the possible frequencies, fundamental frequency is V by 4L, that is 80 Hertz. The next possible frequency is 3 times the fundamental, that is 240. And the next possibility is 5 times the fundamental. So 5 into 80 means 400. Next, 7 times. So 7 into 80 means 560 Hertz, like that. Okay, here we have 80, 240, then 500 and 400. 80 is possible, 240 is possible, 400 is also possible. So A, B and D are possible. Okay, next. See, in a long cylindrical tube, the water level is adjusted and the air column above it is made to vibrate in unison with a vibrating tuning fork kept at the open end. Maximum sound is heard when the air column length are equal to. See, first resonance will occur when the length of the air column is equal to 1/4 of the wavelength. Okay, the wavelength produced by the excited tuning fork. Second resonance will occur when the length of the air column is equal to 3 lambda by 4, and third resonance will occur when the length of the air column is equal to 5 lambda by 4. So lambda by 4, 3 lambda by 4 and 5 lambda by 4. See, the air column can vibrate only with the anti-node at the open end and node at the closed end. Okay, so this is the minimum number of waves that can be accommodated. Okay, when the number of waves are minimum, see, you have to understand the wave. See, we could accommodate only minimum number of waves because the waves are so big. Or let us say wavelength is maximum. When the wavelength is maximum, frequency is minimum. So this is the minimum possible frequency with which this system can vibrate. Okay, and this is the next possibility, and this is the second possibility. Okay. If L1 and L2 are the length of air column for the first and second resonance when a tuning fork of frequency N is sounded on a resonance tube, then the distance of the displacement antinode from the top end of the resonance tube is. See, this is the case when first resonance occurs. See, lambda by 4 is equal to the length of the air column. But we will be measuring only the length of the pipe. And see, actually the reflection will take place not exactly at the ends but slightly beyond. So lambda by 4 will be equal to L1, that is the length of the pipe, plus N correction represented by small e. So this is the case when first resonance occurs, and this is the case when second resonance occurs. See, the second resonance length is L2, so 3 lambda by 4 will be L2 plus E. Okay, N correction will be same in both the cases. Okay, so from here we will get, see this N correction as L2 minus 3 L1 divided by 2. Because here we have L2 plus E, that is actually L2 plus E is 3 lambda by 4, 3 I have written here. Now this lambda by 4 can be replaced by L1 plus E. Okay, so 3 L1 plus E. Okay, now let me take this L2, this 3 L1 onto the left. So L2 minus 3 L1. On right side we will have 3E. When this E is taken to the right, it will become minus E. So 3E minus E will be 2E. So 2E will be L2 minus 3 L1 and E equal to L2 minus 3 L1 divided by 2. That is the N correction. Now a tuning fork of frequency 340 Hz is vibrated just above a cylindrical tube of length 120 cm. Water is slowly poured in the tube. If the speed of sound in air is 340 meter per second, then the minimum height of water required for resonance. See, lambda equals V by nu and frequency is 340. So 340 over 340, that will be 1 meter. Resonance can occur when length of air column is lambda by 4 or 3 lambda by 4 or 5 lambda by 4. Like that. See, lambda is 1 meter and lambda by 4 will be 25 centimeter. So first resonance will occur when the length of the air column is 25 centimeter. Then the length of the water column in the tube, that will be 120 minus 25, that will be 95 centimeter. Second resonance will occur when lambda by, see, when length of the air column is 3 lambda by 4, that is 3 into 25 or 75 centimeter. Then the length of the water column will be 120 minus 75, that will be 45 centimeter. So the minimum height of water required for resonance, that will be 45 centimeter. Okay. Now see, a student is experimenting with a resonance tube apparatus in physics lab to find the speed of sound at room temperature. He got resonating length of air column as 17 cm and 51 cm using tuning fork of frequency 512 Hz. Find the speed of sound at room temperature and specify whether the side water reservoir was moved upward or downward to obtain the second resonance. See, speed of sound, that is given by V equal to nu into L2 minus L1, and see, L2, that is second resonance length 51, L1 is 17. Okay, that is in centimeter. We can convert this into meter by multiplying with the 10 raised minus 2, and frequency of the tuning fork is 512. So if we multiply this, we will get 348. Now see, 348 meter per second, and side reservoir is to be moved downward, okay, to obtain the second resonance, because we will have to increase the length of the air column. Okay, so to be moved downwards. While measuring the speed of sound by performing a resonance column experiment, a student gets the first resonance condition at column length of 18 cm during winter. Repeating the same experiment during summer, see the second resonance, see first resonance we will get when length of the air column is lambda by 4, that is 18. Second resonance we will get when length of the air column is 3 lambda by 4, it must be 3 into 18, that is 54. But when temperature is increased, speed will increase and wavelength also will increase. So 3 lambda by 4 will be more than 54 centimeter at a higher temperature. Okay, so see, student measures the column length to be x centimeter for the second resonance at a higher temperature, so that x should be more than 54, right? This one. Next, a tuning fork of frequency 480 Hz is used in an experiment for measuring speed of sound in air by resonance tube method. Resonance is observed to occur two successive length of the air column 30 and 70 centimeter. Then V is equal to, see, V equal to 2 nu into L2 minus L1. Frequency is given as 480. L2 is 70 centimeter, or we can represent it as 0.7 meter. L1 is 30 centimeter or 0.3 meter. So we will get 384 meter per second. Okay, this one. Next, a student is performing the experiment of resonance column. The diameter of the column tube is 6 centimeter. The frequency of the tuning fork is 504 Hz. Speed of the sound at the given temperature is 336 meter per second. The zero of the meter scale coincides with the top end of the resonance column tube. The reading of the water level in the column when the first resonance occurs. See, lambda by 4 is actually length of the air column plus n correction. There is an empirical formula for n correction in terms of the diameter of the pipe, that is 0.3d, and diameter is given as 6 centimeters, so 0.3 into 6, that is 1.8 centimeter. See, lambda is equal to speed divided by frequency, 336 over 504, and it is 2 by 3 meter. And L1, that is actually lambda by 4 minus n correction. Okay, lambda is 2 by 3 meter. We can convert it into centimeter by multiplying 100, and we have to take 1/4 of it. So this is lambda. Okay, into 1 by 4 will give lambda by 4, and n correction is 1.8. So we will get 14.9 centimeter. 14.9 centimeter, this one. In an experiment to determine the velocity of sound in air at room temperature using a resonance is observed when the air column has a length of 20 centimeter for a tuning fork of frequency 400 Hz is used. The velocity of the sound at room temperature is 336 meter per second. The third resonance is observed when the air column has a length of, see, lambda by 4 in case of the first resonance, that is equal to first resonance length plus n correction. Okay, this L1 is given as 20 centimeter. Okay, and speed is 336. The frequency of the tuning fork used is 400 Hz. So lambda by 4, this V by nu is actually lambda. So V by 4 nu will be lambda by 4. So 336 divided by 4 into 400. This is lambda by 4 in meter. We can convert it into centimeter by multiplying with 100. So we will get 21. Lambda by 4 equal to 21. See, in which L1 equal to 20. So n correction will be 1 centimeter. See, second resonance will occur when the length of the air column is 3 lambda by 4, and third will occur when the length of the air column is 5 lambda by 4. So for third resonance, L3 plus n correction, that is equal to 5 into lambda by 4. Lambda by 4 we have got 21. That will be 105 centimeter. In which n correction is 1 centimeter, so L3, third resonance length will be 104 centimeter, this one. Okay. Next, see, the first resonance length of a resonance tube is 17 and the second resonance length is 53. The third resonance length of the tube will be, see, n correction we will get 53, this L2 minus 3 L1 by 2, that is 1 centimeter. Okay. So the first, this lambda by 4 will be L1 plus E. L1 we have got 17 centimeter. Okay, so 17 plus 1, 18 centimeter, that is lambda by 4. Okay, so the third resonance length will be 5 lambda by 4. That is equal to L3 plus E. Okay, that is equal to 5 into 18, that is 90. So L3 will be 89 centimeter. Okay, 89 centimeter. Next, specific heat capacity of solids and liquids by the method of mixtures. So first see, equal amount of heat energy are transferred into equal mass of ethyl alcohol and water sample. The rising temperature of water sample is 25 degrees Celsius. The temperature rise of ethyl alcohol will be. It's given that specific heat capacity of ethyl alcohol is half the specific heat capacity of water. Means a given quantity of heat is added to equal quantity of or equal masses of water and ethyl alcohol. The rising temperature observed in water is 25 degrees Celsius. Then what would be the rising temperature in ethyl alcohol? That's the question. See, delta Q, this is the heat absorbed. That is equal to MC delta T, where delta T is the rising temperature. See, M is the mass of ethyl alcohol. C is the, here M is the mass of water. C is the specific capacity. Delta T is the rising temperature. See, this is for water. Okay, and here this is for the same mass of ethyl alcohol. Specific heat capacity is half that of water. So delta T we will get 50 degrees Celsius. This one. Okay. Now, see, a block of mass 2.4 kilogram is heated to temperature of 500 degrees Celsius and placed on a large ice block. What is the maximum amount of ice that can melt? Specific heat for the block is 0.1 calorie per gram per degree Celsius. See, when that block cools from 500 degrees Celsius to 0 degrees Celsius, heat released by it, that is we have to find by using the formula MC delta T. See, it's of mass 2.4 kilogram, means it is 2400 gram. Specific heat capacity is 0.1 calorie per gram per degree Celsius and its temperature falls from 500 to 0. So the change in temperature is 500. Mass, specific capacity C and delta T. This is the heat lost by the hot body. That heat is being absorbed by ice. See, the heat required to melt 1 gram of ice is 80 calorie. Suppose m gram ice melts, or m gram ice at 0 degrees Celsius is converted to water at 0 degrees Celsius. So the heat absorbed will be m into 80. Okay, so the heat released by this hot body as it cools from 500 degrees Celsius to 0 degrees Celsius is just sufficient to melt m gram of ice. Then that m will be 1500 gram or 1.5 kilogram. Okay, this one. 10 gram of ice at 0 degrees Celsius is kept in a calorimeter of water equivalent 10 gram. How much heat should be supplied to the apparatus to evaporate the water thus formed? See, we have 10 gram of ice. First, we have to convert that solid ice at 0 degrees Celsius to water at 0 degrees Celsius. The heat required will be 80 calorie for each gram. 10 gram we have to convert, so 10 into 80. This is the heat required to melt the given mass of ice. Okay, so we have got ice or water at 0 degrees Celsius. That is to be, its temperature is to be increased to 100 degrees Celsius. Not only that 10 gram of water, we will have to heat the calorimeter also. That heating that calorimeter is equivalent to heating 10 gram of water. We have 10 gram of water and calorimeter equivalent to another 10 gram of water. So it is equivalent to heating a total of 20 gram water. So mass of water 20 gram, specific heat capacity 1, its temperature is to be increased from 0 to 100. That is 100 degrees Celsius. Okay. Next, see, water is to be evaporated. Okay, or we have to convert that 10 gram of water at 100 degrees Celsius to steam at 100 degrees Celsius. See, for the conversion of each 1 gram of water from 100 degrees Celsius to steam at 100 degrees Celsius, heat is 540 calorie. So to convert 10 gram, the heat required will be 10 into 540. Okay, so this is 5400 and here it will be 2000. So 7400 and here it will be 800. So total 8200. Okay, 8200 calorie, this one. Okay, 1 kilogram of ice at 0 degrees Celsius is mixed with 1 kilogram of steam at 100 degrees Celsius. What will be the composition of the system when thermal equilibrium is reached? Latent heat of fusion of ice is given. Latent heat of vaporization of water is also given. But it's simpler and easier to calculate this in CGS system. Suppose 1 gram of ice at 0 degrees Celsius is mixed with 1 gram of steam at 100 degrees Celsius. So what is true for 1 gram ice and 1 gram steam must be true for any equal masses of ice and steam. Okay, now see in CGS system, the latent heat of fusion of ice is 80 calorie per gram and the latent heat of vaporization of water is 536 calorie per gram, and you can take it approximately 540 calorie per gram. So, heat required to convert 1 gram of ice at 0 degrees Celsius to water at 100 degrees Celsius is 180 calorie. See, 1 gram ice can be melted by using 80 calorie. We will get 0 degree water. At that 1 gram water at 0 degrees Celsius can be heated to 100 degrees Celsius by giving 100 calorie of heat. So to convert 1 gram ice at 0 degrees Celsius to 1 gram water at 100 degrees Celsius, total heat required is 180 calorie. When 1 gram steam condenses, it will release 540 calorie. When 1 by 3 gram steam condenses, it will release 540 by 3, that is equal to 180 calorie. So when we put 1 gram of ice to a container, see, filled with 1 gram steam at 100 degrees Celsius, then as soon as we put 1 gram ice, 1 by 3 gram of steam will condense. It will release 180 calorie of heat, and that 1 by 3 gram steam will get converted as 1 by 3 gram water at 100 degrees Celsius. The heat released, this 180 calorie, will be absorbed by ice, and that ice will get converted as water at 100 degrees Celsius. So this is 1 gram water at 100 degrees Celsius, and it is due to the melting of ice. This is 1 by 3 gram of water at 100 degrees Celsius, and it is due to the condensation of steam. The remaining 2 by 3 gram will remain as steam at 100 degrees Celsius. So the mixture will contain 4 by 3 gram of water at 100 degrees Celsius and 2 by 3 gram of steam at 100 degrees Celsius. See, what is true for 1 gram ice and 1 gram steam must be true for any equal masses of steam and ice. See, in the given example, we have 1 kilogram ice and 1 kilogram steam at 100 degrees Celsius. So the see, at equilibrium, the mixture will contain 4 by 3 kilogram of water at 100 degrees Celsius and 2 by 3 kilogram of steam at 100 degrees Celsius. Okay, 2 by 3 kilogram means 665 gram steam, and 4 by 3 kilogram means 1335 gram of water. Okay, now see, this is the calculation done in SI system. This is the heat required to melt 1 kilogram of ice. Okay, by absorbing this much heat, 1 kilogram ice at 0 degrees Celsius will get converted as 1 kilogram water at 0 degrees Celsius. Okay, see, this is the heat required to raise the temperature of 1 kilogram of water from 0 to 100 degrees Celsius. So this much is the total heat required to convert 1 kilogram of ice at 0 degrees Celsius to water at 100 degrees Celsius. Okay, now see, when 1 kilogram steam condenses, it will release 2.26 into 10 raised to 6 joule, or this can be expressed as 22.6 into 10 raised to 5 joule when 1 kilogram steam condenses. When 1 by 3 kilogram steam condenses, just 1/3 of this, that is 22.6 into 10 raised to 5 divided by 3, and this will be exactly equal to this one. Or the heat released by the condensation of 1 by 3 kilogram of steam at 100 degrees Celsius will be just sufficient to convert 1 kilogram of ice at 0 degrees Celsius to 1 kilogram of water at 100 degrees Celsius. Okay, next let's see. A copper ball of mass 100 gram is at a temperature capital T. It is dropped in a copper calorimeter of mass 100 gram filled with 170 gram of water at room temperature. Subsequently, the temperature of the system is found to be 75 degrees Celsius. Okay, what we have to find? We have to find capital T. See, heat lost by the hot copper ball will be equal to the heat absorbed by the calorimeter and the water in the calorimeter. Okay, now see, we have a copper ball of mass 100 gram and its specific heat capacity is 0.1 calorie per gram per degree Celsius, and it cools from T to 75 degrees Celsius. Okay, and 100, that is the mass of the copper calorimeter, and its specific heat capacity is again 0.1, and it gets heated from the room temperature 30 degrees Celsius to 75 degrees Celsius. So this is MC delta T for calorimeter, and that calorimeter contains 170 gram of water, mass of water, specific heat capacity of water, and that water gets heated from room temperature 30 degrees Celsius to 75 degrees Celsius. So here we will have 45 into 170, and here we will have 45 into 10. So 45 we can take common, then 170 plus 10, that is 180 into 45. And on the left side we will have 10t minus 75 into 10, that is 750. And see, this 750 can be taken to the right side, so we will get 15 can be taken as common factor, so 15 into 50 plus 540, that is 15 into 590. Okay, so T will be 15 into 59, and that is 885 degrees Celsius. Okay, now let's see what we have next. The amount of heat required to convert 1 gram of ice at minus 10 degrees Celsius into steam at 100 degrees Celsius. See, ice at minus 10 degrees Celsius means it is to be heated to 0 degrees Celsius. Okay, so we have to apply delta Q equal to MC delta T. Mass of ice is 1. Specific heat capacity, half the specific heat capacity of water, that is 0.5 calorie per gram per degree Celsius, and it is to be heated from minus 10 to 0 means the rise in temperature will be 10 degrees Celsius. Okay, so this is the heat required to increase its temperature from minus 20 to 0. Then we will have to supply the latent heat, that is the heat required to convert 1 gram ice at 0 degrees Celsius to 1 gram water at 0 degrees Celsius, that is 80 calorie. Okay, then the temperature of 1 gram water is to be increased from 0 to 100. So again we have to apply the formula delta Q equal to MC delta T. Mass is 1 gram, specific heat capacity is 1 calorie per gram per degree Celsius, and delta T is 100. So we will get 185 calorie. 1 calorie is equal to 4.2 joule. So 185 into 4.2, that will be 721 joule. Okay. Now let's see, 2 kilogram ice at minus 20 degrees Celsius is mixed with 5 kilogram water at 20 degrees Celsius. Final amount of water in the mixture. Specific heat of ice is given, specific heat of water is given, latent heat of fusion of ice is also given. We have 5 kilogram of water at 20 degrees Celsius. When it cools from 20 degrees Celsius to 0 degrees Celsius, heat released will be, let's calculate in calorie. So the kilogram is to be converted into gram. 5 kilogram means it is 5000 gram. So the mass is 5000. Specific heat capacity of water is 1, and delta T means it cools from 20 to 0. So delta T is 20. So this is 10 raised to 5 or 1 lakh calorie. Okay, now using this we have to increase the temperature of 2 kilogram ice from minus 20 to 0 degree. Okay, again we have to apply the formula delta Q equal to MC delta T. 2 kilogram means 2000 gram. Specific heat capacity of ice is half the specific heat capacity of water, that is 0.5, and its temperature is to be increased from minus 20 to 0. Okay, so the rise in temperature will be 20. So 20,000 calorie of heat is required to increase the temperature of ice from minus 20 degrees Celsius to 0 degrees Celsius. We see this 5000 gram of water, when it cools from 20 to 0, it releases 10 raised to 5 calorie, of which 20,000 will be used to increase the temperature of ice from minus 20 degrees Celsius to 0 degrees Celsius. Okay, now we have 80,000 calorie of heat and 2 kilogram of ice at 0 degrees Celsius. Okay, see, to convert 1 gram of ice at 0 degrees Celsius to water at 0 degrees Celsius, heat required is 80 calorie. To convert 1000 gram of ice at 0 degrees Celsius to water at 0 degrees Celsius, the heat required will be 80,000. Okay, actually we have 2 kilogram of ice and 80,000 calorie heat. Using that 80,000 calorie, we will be able to convert only 1 kilogram of ice at 0 degrees Celsius to water at 0 degrees Celsius. Okay, so the remaining 1 kilogram ice will remain as solid ice. Okay, so finally, see, 1 kilogram ice will melt already. There is 5 kilogram water and 1 kilogram water will be produced due to the melting of ice, and 1 kilogram ice will remain as solid ice. Okay, so the total mass of water in the mixture will be 6 kilogram. Okay. Now let's see the latent heat of vaporization for the 1 gram of water is 536. Its value in joule per kilogram. See, 536 calorie means it is into 4.2 joule. That much is the heat required to convert 1 gram of water to steam. But we require the heat to convert 1 kilogram. So this is for 1 gram. So into 1000 will give you for 1 kilogram. That we will get 2.25 into 10 raised to 6. Okay.